Hi everyone, welcome to the Ultimate TypeScript Game Dev course. In this course, we will first build a simple Sonic Infinite Runner game. Then we will move on to a more complex project by building a clone of the classic Nintendo game Duck Hunt. Finally, we will build a Kirby-like platformer where you will learn how to use an external visual editor called Tiled to make your levels and how to render them in your TypeScript game. Subscribe and like for more tutorials like this. Before we proceed, I just want to mention that you can access exclusive tutorials on Patreon. Link is in the description. Now, let's get started. Hi everyone. In this tutorial, I'll teach you how to make a simple Sonic-themed Infinite Runner game in TypeScript using the Kirby-like Game library. In this game, you need to collect as many rings as possible. Jumping on enemies grants you a bonus of 10 rings. Continually jumping on enemies without touching the ground gives you a multiplier on each enemy, and the first enemy grants you plus 10, the second plus 10 times 2, the third plus 10 times 3, etc. So the challenge comes from the game getting progressively faster, making it harder to avoid getting hit by enemies. I really recommend playing the game to have a better idea of what we're going to build. The live demo is in the description. So what are the prerequisites for this tutorial? I expect that you have basic familiarity with TypeScript, and if not, at least JavaScript. So if you know JavaScript, it could be your first TypeScript game, so it's okay to follow this tutorial. Because while we were going to write the game in TypeScript, it's going to be very easy TypeScript code, since we will rarely, if ever, need to write custom types. You should be familiar with Node.js and NPM and have them installed on your machine before following this tutorial. However, I do not expect you to know Kirby, so this is what we're going to teach in this tutorial as well. So what is Kirby in the first place? So Kirby is an open source library for making games in JavaScript and TypeScript. So compared to the more popular Phaser JavaScript game framework, its API is a lot simpler, making it very easy for beginners to pick up. It also offers a lot of pre-made functionality out of the box, and therefore you spend less time reinventing the wheel. For those familiar with the Godot game engine, you might be accustomed to the concept of nodes, which acts as building blocks containing out-of-the-box functionality. Kirby has a somewhat similar concept to nodes called components. So in the description, I'll put also the link to the Kirby website if you want to check the docs. So let's set up our project. So create a folder called Sonic-Runner and cd into it using your terminal of choice. And then run the command npm create vite@latest dot. So this command will scaffold a TypeScript project within the existing folder you're using with the popular build tool Vite. So once the command runs, you'll be presented with the following. So pick the vanilla option, and you'll be presented with another menu to choose between JavaScript and TypeScript. Of course, since this is a TypeScript tutorial, select TypeScript. Now let's install the Kirby library. We will install a specific version called v3000.0.16. So run the following command. This version is the latest stable version available at the time this tutorial is being recorded. As long as you stick with this specific version, you shouldn't have issues following this tutorial years into the future. Now, once installed, take a look at your package.json file in your projects folder. You'll notice that Kirby was added to your dependencies. When we used the npm create command, Vite created a bunch of files. Make sure that you have the following project structure. Remove everything within the src folder as we're going to write everything from scratch. Once everything is removed in src, create two files within, one named Kirby ctx.ts and the other called main.ts. You should have now the following project structure. Finally, the last step of our setup is to bring in our game assets. Copy the contents of the public folder provided in the game's final source code, which is available on GitHub, and you'll find it in the description. And you'll find the repo in the description. After having done so, you should have the following files in your public folder. Now let's initialize our canvas. So now that our setup is complete, we can initialize an HTML canvas in which the game will be rendered. This will be done through Kplay by initializing our context, which will allow us to use Kplay functions. In Kplay ctx.ts, which stands for Kplay context, write the following code. So our context is created by calling the Kplay function and passing an object containing various options we want to configure for our game. We first set the width and the height of the canvas. We set the letterbox property to true, allowing our game canvas to scale regardless of the screen size while still retaining its aspect ratio. We set the global property to false so that the Kplay functions can only be used via the constant k. This will lead to more legible code, since you'll be able to easily detect if a Kplay function is in use by noticing k dot the name of the function. We pass an object to the buttons property to define the jump action of our game. Since we want to make the game playable on both desktop and mobile, we set the jump custom action to be mapped to the space key or the left mouse click. Jump is an arbitrary name, and you could have decided on something different. You can also add an arbitrary amount of actions depending on your game's needs, and by adding a new property. For example, you could have a move left property action and then specify the keys you need. The touch to mouse property is used to convert touch input to mouse clicks so that the game is playable on mobile. The debug property is used to toggle on and off the Kplay's debug mode. This mode can be accessed on the web page the game is running on by pressing the F1 key or the Fn and the F1 key at the same time on a Mac. It will display an FPS counter along with the game object's hitboxes, which will make debugging easier. We will use it later in this tutorial. So here we're setting debug to true so that the debug mode is accessible. One thing to note is that by default, debug mode is available, so you don't need to use the property initially. The reason I include it here is that when you ultimately deploy your game, you might not want your players to access this mode. Therefore, setting this property to false before deployment is a good idea. So it's just a way to remember that, hey, there is a debug mode to deactivate before going to prod. Finally, to make the game display sharply regardless of the screen, we set the pixel density property to correspond to the pixel ratio of the current screen. You will notice that not using this property will make the game render slightly blurry on certain screens. We then export the constant k containing a reference to the context so that we can use it elsewhere in our code. Now let's create our first game scenes. So our game will have two scenes. The first is where the game takes place, while the second is a game over screen displaying the player's score. In Kplay, you can create multiple scenes using the scene function. In our main.ts file, let's import the Kplay context and create our scenes. Here we created two scenes. The scene function takes as the first param the name you want to use to refer to that scene. The second param is a function that will run when the game enters that scene. Finally, we also need to use the go function to tell Kplay which scene to go to when the game starts. This function is also used to navigate to other scenes when called within a specific scene. We will write the logic for each scene later. Now let's run our project to see if we have correctly initialized our canvas. In your terminal, run the command npm run dev. When you open the localhost address in your browser, if everything went well, you should see a checkered canvas like shown on the screen. If you try to resize your window, you'll also notice that the canvas seems to always preserve its aspect ratio. This is exactly what we want so that the game is playable on any device. Now let's load our assets. In main.ts, we will load the assets we need for the background and the platforms. This will be a good introduction to how assets are loaded in Kplay. Add the following code. Here we use Kplay's loadSprite function. It takes as the first param a string, which corresponds to the name you want to use to refer to that specific sprite/image. And for the second param, the function expects the path to the asset. Note that we don't need to add the public folder to the path, since Vite makes sure to make whatever is in that folder accessible as if it was placed at the root of the project. So now let's implement an infinite scrolling background. So in our game, the city background must scroll indefinitely. Let's implement this in our game scene. add the following code in main.ts. Let's break it down. To achieve an infinite scrolling background, we need to display the same background image twice. The trick is to reposition the first image behind the second one once it leaves the screen. The second image becomes the first, and the first becomes the second. The same logic is repeated indefinitely. So I previously wrote a post specific to infinite backgrounds with easy to understand visuals, so you can check it in the description as well. In the code above, we first set a constant holding the width of the background image when scaled by 1.5, which corresponds to 1920 by 1.5, which gives us 2880 or 2080, since the original image has a width of 1920. This is needed so that we can position the second copy right after the first one without leaving any gaps. We will display the background at 1.5 its original scale so that it looks nice within our game. We then set an array containing two copies. The two copies. Each copy is created using Kepler's add function, which creates a game object, one of Kepler's major concepts. So what are game objects and components in Kepler? A game object represents an entity rendered on the canvas and is composed of components. These components determine various methods and features that it has access to. Kepler provides these components out of the box, but you can also create custom ones if you wish to. We won't really do this in this tutorial. So the add function used to create game objects takes an array of Kepler components, and let's break down the four we use here. So the sprite component renders a game object as a visible sprite/image. The pause component sets the position of a game object on the canvas using XY coordinates. In Kepler and in many other game libraries, the X coordinate increases the further you go right, and the Y coordinate increases the further you go down. The origin, which is x equals 0, y equals 0, is set at the top left corner of the canvas. The opacity component sets the opacity of a game object using a value between 0 and 1, and the closer the value is to 0, the more it becomes transparent. And finally, the scale component sets the scale of a game object. It is often used alongside the sprite component to change the sprite/image's size on the canvas. As you can see, the second copy uses the same components. However, we set the position differently so that it is rendered right behind the first one without leaving any gaps. Now let's implement movement with an onUpdate loop. While creating game objects using the add function will render them on the canvas, no movement will occur without an update loop. If your game runs at 60 FPS, the loop will run 60 times per second. In Kepler, we use the onUpdate function to set our update loop. We first check if the background image second copy's X position is inferior to 0. In that case, we can assume that the first copy is off screen, and therefore we can safely attempt to move it behind the second copy. This is achieved by setting its position using the move_to_Kepler method made available due to using the positional component, the pause component, when the game object was first defined. Using the shift array method, we delete the first element from the array and return it. Finally, we push it back to the array so that the first copy is now placed as the second element of the array, making it become the second copy. Another if statement is used to make sure the result of shift is not undefined before pushing it to the array again. Otherwise, TypeScript will complain, and rightly so. Regardless of all the above, on each iteration of the loop, we move both copies to the left by using the move_Kepler method on the first copy and the move_to method on the second copy to follow the first copy. Both these methods exist because we used the pause component when creating each respective game object. The move method takes two params, The first is for setting the velocity of the game object on the x-axis, while the second sets the velocity on the y-axis. By setting the x velocity to minus 100 and the y velocity to 0, we're moving only to the left at a velocity of 100 pixels per second. If you're accustomed to other game engines/frameworks, you might have noticed the absence of delta time, corresponds to the time elapsed since the last frame in our game loop, being used to make our movement frame rate independent. This is because the move method takes care of it under the hood. Now, looking at your browser tab, assuming that you have localhost running, you should see the city background scrolling indefinitely. To make the background less distracting during gameplay, I opted to set its opacity to 0.8 instead of 1. Now, if you go back to Caplay ctx.ts, we can set the background of the whole web page to be black. This will result in the city background becoming darker and therefore less distracting during gameplay. We provide to the background property an array of 3 elements, each representing one of the RGB color channels. Each element's value can vary between 0 to 255. This is what's used to represent color. If you check your browser tab, you should notice that the city background is now darker. Now let's implement an infinite scrolling platform. Our game is based on one big illusion. Sonic isn't actually running. The platform on which Sonic stands isn't actually moving. The only thing moving are the background and the platform's image, which are made to scroll indefinitely. If we were to remove all of the game's graphics, we would be left with a game object representing the player that can jump up and land on a static floor. Our goal at the moment is to implement infinite scrolling platforms the same way we did for the city background. The only difference is that the scrolling speed will increase the further the game progresses. In main.ts, add the following code. We first set a game speed variable that is incremented every second using Caplay's loop function. This is similar to JavaScript and TypeScript's setInterval function. The first param is for setting the time between each call, and the second param is the function that will be called. Similarly to the city background, we create 2 copies of the platform's image so that we can achieve infinite scrolling. Platform width corresponds to the final width of the platform's image after scaling it twice. This is because we need to make the platforms bigger in our game to make it look good. We use this constant to know where to place the second copy behind the first one without leaving any gaps. The update logic is also similar. The only difference this time is that the move function takes the game speed variable as the x velocity, allowing for it to increase the platform's speed through time. If you run the project now, you should notice the platforms scrolling slowly and then gradually increasing as the time passes on. Now that we have our game scene mostly done, we're ready to work on adding Sonic to our game. Sonic, the rings he must collect, and the enemies are all entities. Let's create a file named entities.ts in the src folder. Then let's create a game object that will hold Sonic's logic. In entities.ts, add the following code. Now let's break it down. We first import the Caplay context to be able to use the library's function in this file. We then import 2 types, vector2 and game object, or game objet. As you can see, Caplay offers TypeScript types you can use, making development in TypeScript smoother. We then create a function whose sole purpose is to create and return our Sonic game object. You can think of it as our constructor. We enable the function's caller to set the position of the game object before it's created. Positions in Caplay are vector2s, stands for vector2, basically. vec2s stands for vector2. It's a data structure offered by Caplay which has 2 elements, the x and y coordinates. We use the sprite, scale, area, anchor, pause, and body components to compose our game object. Note that generally the pause component can be passed the x and y coordinates as 2 distinct params, or be passed a vector2 containing both at once. In our code above, we opted for the latter, while with our background and platforms game objects, we opted for the former. In the case of the sprite component, we not only display a sprite, but set an animation. You might be wondering, where does this Sonic sprite and run anim comes from, since we haven't loaded anything like that at the moment. Indeed, we put the cart before the horse in this case, so let's add the asset loading logic in main.ts. it will be a great opportunity to explain how animations work in CoPlay. The loadSprite function can take an object as an optional third param used for telling CoPlay how to split an image into individual frames. When an image contains multiple sprites, it is often referred to as a sprite sheet. In our case, Sonic's sprite sheet looks like this. We have a total of 16 frames, which can be viewed as a grid of 2 rows and 8 columns. The object passed to loadSprite must first tell CoPlay how to slice the image using the slice X and slice Y properties. Slice X corresponds to the number of columns, while slice Y corresponds to the number of rows. Then an anims object can be configured to set the animations we need and tell CoPlay which animation is composed of which frames in our sprite sheet. If we take a look at the definition of the run animation, the from property holds the number of the starting frame of the animation, while the to property holds the number of the last frame. When CoPlay slices the image into individual frames, it assigns a number to each of them starting from 0 and counting from left to right, top to bottom. The loop property set to true makes the animation run indefinitely unless manually stopped, while the speed property is used to set its frame rate. The frame rate values used in the code above are arbitrary. I came up with these values based on what looked good during gameplay and after tweaking values. For more details on how animations work in CoPlay, I have again written a post that you can find in the description. Looking back at the components used for creating the Sonic game object in entities.ts, you'll notice that the sprite component takes as the first param the name of the image you want to display, while the second param can be used to set the default running animation. We use the scale component to increase the Sonic sprite size by 3, which is what looked good during gameplay. Now, you might be wondering how hitboxes are created in CoPlay. So the array component is very useful because it allows us to easily create a hitbox for our player, enabling us to call methods like onCollide, onCollideEnd, etc. useful for dealing with collisions. In CoPlay, just passing the area component to the components array is enough to create a box surrounding the player's sprite if the sprite component is also used. You might need in some case to configure the position, width and height of the hitbox, but in our game this isn't necessary at the moment. We will tackle this later. Now that we have used the array component, we can use the anchor component to set the origin of our game object. By default, game objects are rendered starting from their top left corner. This might not be very intuitive for game objects representing characters. That's why I like to use the anchor component in those cases to set the center as the origin instead. Finally, the body component is used to give the game objects a physics body, allowing them to be affected by gravity. Using the body component is crucial since it will give us access to the jump method, which allows us to implement jumping in our game, on our game object. In our body component usage, we set the game object's jump force to be 1700. This is an arbitrary value which I arrived at after extensive testing during gameplay. So those are values that you just tweak around until you find what feels good. Now, how do we add methods to a game object? I explained earlier that a game object is composed of components. However, the add function, which takes in an array of components, can also be passed to that same array a JS object that you can use to set custom properties and methods for that game object. So here we have an object containing two custom methods. The first one is used to set the player controls, while the second is used to set what happens when Sonic hits the ground after jumping. In these methods, we can use the this keyword to access the Sonic game object. In TypeScript, we need to specify what this is. This is done by creating a this param and typing it using the game objet type definition imported from CoPlay. When TypeScript is compiled to vanilla.js, this param will be removed. Taking a closer look at our custom set controls function, we can see that we call an on button press CoPlay function. As the name implies, this is used for handling when a specific button is pressed. It takes as the first param the name of the button you want to listen on. The second param is the function that will fire when that button is clicked. If you remember, the jump button was defined in our Kepler context. This is where you need to define all of the buttons you need for your game. Within our on button press, we check if the player is on top of a static game object using the isGrounded method, which is available because Sonic has the body component. At the moment, we haven't defined any static game objects, but we will create one later. When the player is indeed grounded, we can set the jump animation to play, make the player jump with the jump method, and finally play a jump sound using Kepler's play function, which is used to play audio. Unfortunately, it's very easy to confuse the play method, which is used on game objects for playing animations, versus the play function, which is used for sound. By the way, we need to load the jump sound in main.ts for it to work here. Add the following. The reason why we make sure the player is grounded before allowing any jump logic to run is so that the player can't jump indefinitely, making them able to fly away. Our second custom method is used to set event logic. In Kepler, when a game object has the body component, you have access to the onGround event method. That method runs a function every time the player hits the ground, meaning collides on top of a static game object. When the player jumps, the jump animation plays indefinitely. We want to switch back to the run animation as soon as the player lands back. The code you see on the screen achieves this. To summarize, set controls and set events are custom methods we decided to create on our Sonic game object. They could have been named differently. We could have decided to only have one method that does all of the required logic. This is up to you when making your own Kepler games. So now let's add Sonic to our game. Let's first create a floor on which to place Sonic. So add the following code. To create a static game object, you simply need to create a game object with an area and a body component. So the floor is going to be a static game object. Within the body component, set the isStatic property to true. We use the rect component to create a rectangular shape, and we use the opacity component to set it to 0 to make it invisible. We also don't assign the game object to a constant since we don't need a reference. If you look at the web page where the game is running, assuming your project is running, you will see that nothing has changed. However, if you activate the debug mode by pressing the F1 key or Fn and F1 at the same time on a Mac basically, you'll see an outline representing the hitbox of the game object we just created. For fun, you can try to put the opacity back to 1 and you'll see a white rectangle at the bottom of the canvas. So in main.ts, add the following code to place Sonic in our game. So what we do here in this code snippet, we call make Sonic and set a position using the vector2 Kepler function. We assign the result to a constant called Sonic, which enables us to call our custom methods set controls and set events, enabling our core player game logic. So now that we have done this, everything should work now, but it doesn't seem so. Why is Sonic hanging in the air? That's because we haven't set our game's gravity. In Kepler, gravity is set per scene using the setGravity function and passing to it a number determining how strong it will be. Add the following code in our game scene definition. I came up with the value 3100 after trial and error. You need to test during gameplay to see if the jump is too floaty or not, and that's how I came up with this value. Now if you run the project, you should see Sonic initially fall on the platforms and immediately start running. You can now jump, and when you do, Sonic should curl into a ball, and you should hear a jump sound. However, as soon as he hits the ground, the run animation should be the one playing. Up to this point, we covered a lot of Kepler-specific concepts, and we made quite a bit of progress on our Sonic game. However, there's still work to do. So we still need to add rings for Sonic to collect, implement a scoring system, add motobug enemies that Sonic can jump on for more rings, and implement a combo system allowing Sonic to earn extra rings by continuously jumping on motobugs before hitting the ground again. So now let's implement rings for Sonic to collect. In entities.ts, add the following code. Import the needed assets in main.ts. Here, the makeRing function creates a ring game object. The offScreen component adds an onExit screen method to that game object, used later in this tutorial, to destroy it once it leaves the screen. Ring here is a tag used to identify the game object in collision logic. which we will later cover. Multiple game objects can have the same tag. In main.ts, add the following logic in the game scene to spawn rings. We created a recursive function called spawnRing. When called, it first creates a ring by calling makeRing. In Kplay, you can set an onUpdate loop specific to a game object that will be destroyed if the game object is destroyed. In that update loop, we make the ring move to the left at the same rate as the game's speed. This will give the illusion that Sonic is approaching the ring, while in reality, it's the contrary. We use the onExitScreen method to destroy the ring when it exits the screen to the left. Using Kplay's rand function, we're able to get a random number between 0.5 and 3, representing the time to wait before spawning another ring. Kplay's wait function is used to only call the spawnRing function once the wait time is elapsed. Now that the rings are spawned, we need to write the logic for Sonic to collect them, which implies needing to keeping track of the score. In main.ts, under our game scene, add the following code. In addition to creating variables related to the score, we create a game object acting as our score UI. Using the text component, we're able to display text on the screen. The second param of that component is used to set the font and sizing needed. Finally, we use the Z component to make sure the score UI is always displayed on top of the other game objects by setting its Z layer to 2. You should have the following result. Now, let's update the score every time Sonic collides with a ring. Add the following code in our game scene. We used Sonic's built-in onCollide method, which takes as the first param the tag of a game object you want to check collisions with. The second param is a function that will run in case a collision does occur. Here we play the ring sound and then destroy the ring game object Sonic collided with. Finally, we increment the score and change the score UI's text to reflect the new score. If you run the game now, you should see the score updating every time Sonic collides with a ring. The code needed for adding enemies to our game is going to be very similar to the one for adding rings. The only difference is that, contrary to rings, if Sonic touches an enemy, it's game over. However, if Sonic jumps on that enemy, the enemy gets destroyed. In entities.ts, add the following code. Here, we defined a function for creating our enemy, the Motobug. We used components that should now be familiar to you. However, you might have noticed that we pass an object to the area component. This is something you can do to define a custom hitbox shape. Here, we're setting the shape of the hitbox to be a rectangle using Kplay's rect constructor. It allows you to set the hitbox origin relative to the game object. If you pass k vector 2 0 0, the origin will be the same as the game objects. The second and third param of the constructor are used to set the width and the height of the hitbox. Once we will add enemies to the game, you'll be able to use the debug mode to view how our hitbox configuration for the Motobugs are rendered. Add the following code in main.ts. The logic for spawning Motobugs is mostly the same compared to the one for rings. However, the Motobugs update loop is slightly different. When the game's speed is inferior to 3000, we make the Motobug move faster than the scrolling of the platforms so that it appears as moving on the platforms towards Sonic. Otherwise, it would look like Sonic's the one moving towards stationary Motobugs. However, when the game's speed gets really fast, it isn't possible to really tell the difference. In that case, we simply make the Motobug move at the same rate as the scrolling platforms. At this point, you should see enemies spawn in your game. At the moment, if Sonic collides with an enemy, nothing happens. Likewise, if he jumps on one. Let's add the following code in main.ts. If you're on the game now, you should be able to jump on enemies, and if Sonic hits an enemy while grounded, you will be transitioned over to an empty game over scene. You'll notice that we added logic to multiply the player's score if they jump on multiple enemies before hitting the ground. We're also registering the current player score in local storage so we can display it later in the game over scene. Since our game is very fast-paced, it's hard for players to keep track of how many rings they're collecting. They would have to look up to the top left of the screen while risking not seeing an enemy in time to avoid it / jump on it. To mitigate this and to give the player a better sense of what they're doing, I opted to display the number of rings collected after every collision with a ring or a jump on an enemy. This will also make combos easier to understand. Add the following code in main.ts. Now if you run the game, you should see a +1 appear every time Sonic collides with a ring, and a +10 ×2 ×3, etc. when he jumps on one or many motobugs. An important concept present in the code you see is that game objects can have child game objects assigned to them in Kplay. This is what we do here. Instead of calling the add function to create a game object, we can call the add method to create a child game object of an existing game object. Here we create the ring collect UI as a child of Sonic so that its position is relative to him. Finally, for our game over screen, let's display the player current versus best score and allow them to try the game again if they wish to. In the game over scene code in main.ts, add the following. While it should be relatively easy to figure out what the code you see here does, I'd like to explain what we do here. Using Kplay's getData function, we're able to get the data we previously set in local storage. However, when the player plays the game for the first time, they will not have a best score. That's why we set best score to be 0. If k.getData best score returns null, which is possible. We do the same with current score. Now if you run the project, you should have the following game over screen appear after getting hit by an enemy. After 1 second, you should be able to press the jump button, in our case click or press the space key, to play the game again. Assuming you want to be able to publish the game in web portals like itch.io, you can make a build by creating a vite.config.ts file at the root of your project's folder and specifying the base as /. Now run the command npm run build and you should see a dist folder appear in your project files. Make sure your game still works by testing the build using npm run preview. And finally, once ready to publish, zip your dist folder and upload it to itch.io or to other web game platforms of your liking. Hope you enjoyed learning how to make games in TypeScript with Kplay. If you're interested in seeing more web development and game development tutorials from me, I recommend subscribing to my channel and checking my other tutorials. Thanks for watching. You can watch my beginner React tutorial next. Hi everyone. In this tutorial, you'll learn how to build a clone of the classic Nintendo game Duck Hunt. Our version will be called Duck Hunter. We'll be using the TypeScript programming language and the Kplay game library. In our game, the goal is to shoot ducks using a cursor that's controlled with your mouse, compared to the original game, which was controlled by a gun-like accessory. By the way, you can buy that kind of a gun-like accessory that you can use as a mouse, so maybe you would want to use that for this game, but no worries, it's not mandatory. But if you want to get a closer experience to the original Duck Hunt. So each time a duck is shot, you earn 100 points. There are 10 ducks to shoot every round, meaning that you have 10 tries and 3 bullets on each try. If you successfully shoot all 10 of them, you gain an additional 500 points. Every round, the ducks move faster, making the game more challenging. You can play the game in your browser using the link in the description. Now let's look at the prerequisites for following this tutorial. This tutorial assumes that you are already familiar with modern web development. That means you should know HTML and CSS and of course JavaScript or TypeScript. So in the case if you're coming from JavaScript, so you only know JavaScript, you should be able to follow this tutorial without much trouble because the TypeScript we will write is very simple. It is as close as possible as vanilla JavaScript. So it's just JavaScript with types. You should also know how to use Node.js and NPM, how to use Git, and how to use a terminal, and of course, how to use an editor like VS Code. However, knowledge of the Kplay library is not assumed. The goal is to teach you the relevant Kplay concepts as we go through the project. So you might be wondering what is Kplay in more details. To put it simply, Kplay is an open source library for making games in JavaScript and TypeScript. Compared to the more popular Phaser game framework, its API is a lot simpler, making it easier for beginners to pick up. So by API, I mean how you actually use it, which functions you call, etc. it's relatively easier to pick up than Phaser. It also offers a lot of pre-made functionality out of the box. So that means you spend, therefore, less time reinventing the wheel. For those familiar with the Godot game engine, you might be accustomed to the concept of nodes, which acts as building blocks containing out-of-the-box functionality. So Caplay has a somewhat similar concept to nodes called components. If you want to learn more about Caplay directly from the source, you could check the Caplay docs, which I will link also in the description. So now let's get started. Alright, so to set up a project, first create a folder. That folder can have whatever name you would want to have, and then open it up in VS Code. Once you do so, use the integrated terminal and run the command npm create vite at latest dot. Once you do this and hit enter, you'll be presented with a select a framework options. Select the vanilla option. Once you do so, because we aren't interested in using any framework, front-end framework for this project, since we're using a specific library for making games. So pick the vanilla option. Once the vanilla option is selected, you're going to be asked again to choose a variant, so between TypeScript and JavaScript. Since this tutorial is using TypeScript, select the TypeScript variant. Now, after pressing enter, you'll see a bunch of files being created in your directory. You'll see a public folder, a source folder, a .gitignore, an index.html file, a package.json, and a tsconfig.json. I assume that you have familiarity with modern web development, so I will not go through each of them. So let's get rolling. So now let's install the Caplay library using npm. So to do so, we will use npm install command in the terminal the name of the library, so Caplay, and then the specific version. So the version I want you to use, so by default, you would just write npm install Caplay and then use that as the command for a new project. But let's say you're following a tutorial like you're doing right now. You want to install a specific version so that even in the future, if you watch this tutorial far into the future, whatever I teach in this tutorial will work. So to do so, we were going to use in this tutorial version 3001.0.19, which is the version of Caplay I want you to install. To install it, you use the command npm install Caplay and then type in the name of the version, which is 3001.0.19. Now you might be wondering, like, this is strange. Why are there 3,000 different versions and more? Well, Caplay, the way it works, its versioning system is a bit unconventional. That means version 2 of Caplay is version 2000, and it was when the library was called Kaboom. It was Kaboom 2000, then it got a rebrand and was forked and continued under that new name. So version 3001 could be viewed as the version 3 of Caplay, and it's therefore less daunting than hearing version 3001. Anyway, let's continue. So once you have the libraries installed, I want you to use the link in the description. So I'm going to leave a link in the description with the assets we need for this game, for this project, and place all of these assets under the public folder. So you should have 3 folders within, one called fonts, one called graphics, and one called sounds. And in each of them, you should have, for example, on the fonts one, you should have a Nintendo-NES folder, and within you should have a NES font, which stands for the Nintendo Entertainment System, which was the original game console on which the Duck Hunt game was released on. Then for the graphics folder, you should have a background.png file, a cursor.png file, a dog.png, a duck.png, a menu.png, and a text-box.png. Finally, for the sounds, you should have a bunch of them. I'm not going to list them all, but using the link in the description, you can get everything that you need. Now for the source folder, I want you to actually remove whatever is in that folder. We're going to just write everything from scratch. So the source folder, src folder, is where we're going to write our code. So here, I want you to create 2 files, main.ts and caplay ctx.ts with a capital C. So the first file stands for Kplay context, and it's where we're going to initialize our Kplay library by creating a context that we're going to use in our project, everywhere else in our project, to call various functions related to Kplay. So the way you do this is first you import Kplay from Kplay using this import statement, and then create a constant called k and call the Kplay function, which allows us to create a context for the Kplay library, which essentially means that we're going to initialize our canvas and have now access to all the various functions that Kplay offers that we can use. Now, this could be enough, but we want to specify a few options like the width and the height of the canvas, etc. And for that, you can pass an object to the Kplay function and specify a bunch of properties. So the properties we're going to specify are the following. So first of all, we're going to set a width of 256 and a height of 224, which corresponds to the original resolution of the NES Entertainment System. So actually NES stands for Nintendo Entertainment System. Anyway, so this is going to be the resolution of our game. And then you're going to set the letterbox property to true. This will make sure that the game canvas will scale regardless of the screen size. That means that even if you're playing on a big monitor, it's going to just scale up the canvas so that everything is nicely visible. We're also going to set the touch to mouse property to being true, so that the game will be playable on mobile if someone wants to use their mobile phone to play this game instead of a mouse on a PC. I'm going to scale, using the scale property, the game 4 times so that it looks nicer. We're going to set the pixel density property to be the same as the device pixel ratio. The reason we're doing this is that if you were to not have this option, you're going to realize that on certain screens, for example, on my 4K monitor, the game looks a bit blurry. So by doing this, by setting up the pixel density to be the same as the one from your device, by calling the device pixel ratio, which is, by the way, a variable that is globally available in the browser. So that's why you can just call it here, even though it's defined nowhere in our script, in our file. That's why you can use it. So by using that, we're able to set the correct pixel density so that our game will look sharp in any screen. We also set the debug property to being true. Now, debug mode is a mode offered by Kplay that you can access by pressing the F1 plus the Fn plus F1 key on Mac, or the F1 key on Windows. And you need to do that within the web page in which the game is running, so that it will open a debug mode in which you can see all the hitboxes and debug information and the FPS count, etc. that are very useful information when developing your game. So here, by default, when you just create a Kplay game, this debug mode is enabled by default. But just so that I always explicitly put the property here as true, so that when I actually deploy the game in production, I can remember to set it to false, so that in the final build, when the build that is accessible by players, they will not be able to access the debug mode. Finally, we set the background to being an array of 3 values, which corresponds to the RGB color channels, which varies from 0 to 255 for each of them, and is used to define color. And here I want the background of our web page to be black, so the game will be fully black. Finally, we export the constant by using export default case, so that we can import it in our main.ts and anywhere else we need to call Kplay functions. Now, one thing I forgot to put here is the global property. So you should be careful with that. You should have a global property set to false, so that Kplay functions can only be called by using the k constant. So k dot the name of the function. Here I forgot to do this, so please add it. So that way it's going to keep everything nicely organized, and you won't risk. I would assume if, for example, you're collaborating with others, it might happen that I don't know, they call the Kplay functions directly and it's going to produce a mess. So when you set the global to false, every Kplay function can only be called by using the k constant. So that's something that is really handy. So after having exported the constant, let's go to main.ts and let's import it here. So import k from the Kplay context file. And then here, we're going to define our scenes. So scenes in Kplay can be set using the scene function. So that's why we can do k.scene, and it takes two params. The first one is the name you want to use for that scene, and the second param is the function that will run when the game enters that scene. So for now, let's have a main menu scene with an empty function. Let's have a game scene with also an empty function that we'll fill later, and a game over scene. So those are the three scenes that are going to be useful for our game. The names main-menu, game, and game-over are arbitrary names. You can pick whatever name you want. However, I would assume that if you're following this tutorial, of course, choose the same names as me so that you will not get confused later. Finally, we need to set the default scene. The way we do this in our main.ts file is to call the go function, so the go Kplay function. This function is not only used to set the default scene here, in our case, but also used more generally when you want to go to another scene. So if I were to call this k.go function within a scene, the scene function, then it will be used to go to another scene, etc. So here we call k.go to go to the main menu when the game runs, since main.ts is the entry point of our project. And it has been set up that way by Vite, if you look at the index.html file. So now let's run the project, run the command npm run dev. Once you do this, an address will show up in your terminal. Click on that, and you should be able to see your game, a web page containing your game. For now, let's go back to the Kplay ctx.ts file and let's comment out the background property just so that you can see that by default, Kplay will create a checkered board for the canvas. So that's something just I wanted to show you so that you can differentiate between what is the canvas area and what is just the background of the page. So now let's work on the main menu scene. So first, let's import the menu asset. So basically, an image that said Duck Hunter. And to import or to load assets, you can use, especially images, you can use the Kplay load sprite function. The way it works is that it takes as the first param the name you want to use for the sprite you want to import. So in our case, it's an image, which is the Duck Hunter screen. And here we decided to use the menu as the name. And the second param of the load sprite function is the path where to get that image. One thing to note is that when using a module, a build tool like Vite, you can specify the path as if it were from the root. Despite the fact that our images are within a public folder, Vite will make sure that whatever is in the public folder can be accessed as if it were from the root of our project. That's why I don't need to specify public/graphics/menu.png, and I can just immediately do graphics/menu.png. Now to display a sprite, you need to create first a game object and then use the sprite component on it. So a game object is something very important in Kplay. It's one of the core concepts. The way you create a game object is by using the add function, Kplay function. A game object is composed of components, and Kplay offers a bunch of components, and those components add functionalities and features to your game objects. So for example, the add function we're going to use here to create our first game object is going to be, it takes in an array as the param and an array of components. So the first component we're going to use here is the sprite component offered by Kplay. You can access that by calling k.sprite. And then here, since we have loaded our sprite asset, we can use, since we have loaded our menu, we can use the key we used it for that sprite and use it in the sprite component. So here I can do sprite and then pass in the string menu, and it will display the sprite, the menu image as the sprite of that particular game object we're creating. Now, if you look at the result, you can see that we have a nice looking Duck Hunter title screen. So now let's go back, and by the way, if you press the F1 key or the Fn plus F1 key, you can enter the debug mode, and here you can see at the top left corner an FPS counter telling you the frame rate of your game. Alright, so now we're going to create another game object, and this game object is just going to contain a message, a text to say, like click to start, a message that tells the player to click to start the game. The way we're going to do this is, of course, again, create a game object, and within the game object, use the text component, which is another component you can use. And here, the text component takes as the first param a string, which is the text you want to use, and as the second param, optionally, the font options, the text options to be more precise, where you can specify the font and the size of the font, etc. So here we're writing click to start, and then we're going to, in the font, the text options, we're going to specify the font as being the NES font with a size of 8. Now NES, the string you see here is not defined anywhere, so we need to first load our font. So here I'm going to use k.loadFont, which is again a function created by Kplay. From Kplay, sorry. And it takes as the first param the name you want to use for that font, and then the second param the path. So here again, in the much the same way as with the load sprite, we use here the NES name, so that's why we used the NES name earlier on. And now this should actually display some text with a click to start. We're using the font we specified. Now, before we go and look at the results, let's first set the Z layer. So again, we can do that by using another component offered by Kplay. The Z component allows you to specify the layer on which the game object will be displayed. This is very useful when you want to display objects on top of others. And here we want the text to be on top of this menu sprite so that it is not hidden by it. So by default, I think you could, by default, it's in the rendering is in order of creation of the game object. So because we first had the menu sprite created, the game object with the menu title screen, then if you were to use create the game object with the text, it should normally shouldn't need to specify the Z layer, but I don't remember actually if there were an issue here. So here in the code, I wrote it as I set the layer to being 2, so that I'm sure that it is on top of the title screen. Yeah, by the way, I removed it just right after, so yeah, it's not needed in the end. But however, we're going to use the anchor component instead. So the way the anchor component works is that it is used to center the game object. By default, game objects are rendered from their top left corner. And sometimes you don't want that. You want to render a game object from its center, and the anchor component allows you to specify that. So that instead of rendering game objects from the top left corner, which is something that is, things are usually rendered from the top left corner in various graphics programming environments, so not necessarily just here with Kplay, but if you use any graphics library, or for example, I think P5.js or any other library, usually things are rendered from their top left corner. Now, using the position component, pause, we can set where to place the game object on the screen. Here, as the name implies, as the name of the component implies, a position is in a 2D space is an X and a Y coordinate. So here I'm just gonna use this center. So Kplay offers the center function, which allows you to get the coordinate of the center of the canvas. So by calling k.center, and then the function, you will get a vector2, which contains the x and y coordinate. So here I'm using the x coordinate for the x, the x position, and I'm using the y coordinate of the center plus 40 for the y position of the text of the game object containing the text click to start, so that it appears a bit below the sprite duck hunter, between the image duck hunter. Now we're going to do again another game object, just for crediting, I guess. I wrote made by JS Legend, and then here again the font size, etc., and then the components for the position, etc. Here again the Z layer is not necessary, and one component I want to cover is the color component, which you can use to specify some colors. And that's a good opportunity to create a constants.ts file, and here we're going to create a constant called colors, which is going to be a JavaScript object, and in that we're going to specify the blue color we're going to use for our game. And as we go along in this project, I will add a bunch of other colors to it. So here you can just call it, make sure to import it at the top of the main.ts file, and now we can use colors.blue, and it's going to display this text in blue. And finally, just to not make the text too obvious, I guess, we can specify the opacity of our text using our game object, not just the text, of using the opacity component and setting it up to half, so 0.5, because the opacity component takes a value between 0 and 1. Now, if you look at the browser, you should see a click to start text under the Duck Hunter title screen, and a made by JS Legend at the top left corner, which with a half opacity. Now, because our game is score based, we want to keep track of the score of the player and put their best score in the title screen, a bit like the original Duck Hunt did. So here, let's create a best score variable, and let's use Kepler's getData function, which allows us to get data from local storage. Here, I'm going to get the data from a key called best-score. At the moment, this key does not exist in local storage. By the way, if you're not familiar, local storage is where you can store data in the browser that can be used at a later date. So basically a way to save things. But the problem with that is that it is not really reliable. But since this is just a small score-based game, it's not a big deal, so let's use it here. So here, as I said, we're getting the data from this key, which does not exist yet. And we have a statement here using the two vertical bars to, if this is not defined, which isn't defined the first time you open the game, we should set 0 instead for the best score. Now, I think that we don't need the number typing here. So let's remove it for now. So now what happens here is that the if statement, we're going to have an if statement and check if best score is defined. And if best score isn't defined, actually, I don't think you need that since we set it up to 0 anyway. So yeah. So either you can remove the vertical bar 0 and just keep the if statement, where we just set it to 0 afterwards, since it's a variable. And then we use the setData Kepler function to set the best score key as an actual key in local storage with the value 0. Now, right below it, we create another game object with some text, which will display the top score. Again, the same logic here and components we're using. You should now be familiar with these components. Let's add a new color to our colors constant object in constants.ts, and once we do that, we can use it here. And here we're going to have a utility function. So let's create a utils.ts file, and in that create that function that we're going to use to format the score. So in our game, our score is always displayed with a format that is of 6 digits. So to have this, let's create a function that will take in the score as a number and the number of digits we want to format the score in. So first of all, let's create a constant called score as text and convert our score, which is a number, to a string using the toString function. Then let's have a variable called zeros, or yeah, a variable called zeros to add, which initially is 0, to determine how many zeros we need to add in front of the score so that it fits under the 6-digit format, or the number of digit formats that that we want. So if the score as text.length is inferior to the number of digits, we can determine the number of zeros to add by doing number of digits minus the score as text length. So the length is the number of characters in our score as text, as a string. Now let's create another variable called zeros, which is actually a string, strings that is going to contain the zeros that we need to add as a string to the score. Now we're going to have a for loop, and that for loop will just add zeros to our string. Actually, this is not a good way to do it. Yeah, we should probably just set the zeros to 0 initially, or to, actually we should the 0 we are adding in the for loop should be a string, a 0 in a string. Sorry for that mistake. And now finally, that way we won't need to in the end return the zeros plus a stringified score. Well, actually, we're going to need this, but something to notice is that in JavaScript and TypeScript, you can concatenate a number with a string by just using the plus sign, which is something that is illegal in other programming languages. So I thought I would just use this, convert it to a string before doing this operation, just to make things clearer in case someone who isn't familiar with JavaScript and TypeScript stumble upon my code base, I guess. Anyway, yeah, so once this function is done, let's use it. So import it at the top of main.ts and pass the best score to it with as the second param, not 0, sorry, that's a mistake, 6, which is the number of digits we want to display the score in. And then finally, let's add a onClick handler. So the way you handle events, there are many ways, and for clicking, you use the onClick function provided by Coplay. And it takes a first param, an only param. Actually, yeah, it can take more than one param if I remember correctly. But in our case, we just need to pass to it a function that it will fire when the player clicks. So here we just go to the game scene. So now if I look at the results of that, you can see that if I have the top score displayed in the correct number of digits. All right, so now let's work on the game scene. So in our game scene, which is the whole place where the game takes place, the core of our game, I would say, we're going to first set our cursor using the set cursor Coplay function to none, which will basically hide your mouse cursor when hovering over the canvas. The reason we're doing this is that we're going to later replace it with our own. So our own cursor, which looks like a cross and like a cursor from a gun. Now let's create a game object which is going to be the sky of our game. So the background, the bluish background. So to do so, let's create a game object. That game object is going to use the rectangle component. That component is from Coplay, and you can set the width and height by passing to it the width and the height you want as params. Here we're using the Coplay width and Coplay height function to get the canvas width and height. So it takes the full, it's going to create a rectangle that will take the full width and height of the screen, the canvas. Since I told you that by default in Coplay, game objects are rendered from their top left corner, that means that the game object will be placed at the top left corner also. So not only are objects, the origin of our canvas is the top left corner, so the coordinate 0, 0 is the top left, but also the origin of the game object itself is its origin, so it's top left corner. That's why we can just do the width and the height, and we do not need to specify a given position, because by default in Coplay, if you don't use the positional component, the pause component, it's just going to place the game object at the top left corner of the canvas. Now, just one thing to note is that the way the space works in Couplet is that the further you go to the right, the further the value of X increases. The further you go down the screen, the further the value of Y increases. So that's how it works. Now we can use the color component and specify the blue color. So that's going to be the color of the game object in the rectangle. Then we're going to set a tag. Tags are one of the most useful concepts, features of Couplet. I mentioned that to create a game object, you use the add function, and the add function takes as its param an array of components. But it can also take something that isn't a component, which is a string. And this string is called a tag and basically allows you to identify this game object. That means that later on, if you want to get this game object from somewhere else, you can use Couplet's get function and pass to it the tag, and it will be able to query and get the game object you need. That's why it's very useful to create tags when you want to be able to get an object. And here we're setting the tag as sky because later on in our game we're going to need to change the color of the sky in certain situations, so the background, and that's why it is useful here. So now if you look at the result, when we click on our game, you can see that we are redirected to the game scene and we have a nice bluish background. Now let's create another game object, and this time around it's going to be the background sprite. So if you look at our public folder, you're going to see that it's the bushes, yeah, and the trees, and that's what we need for that. So here again, I use the sprite background, which we haven't yet imported. We're gonna do that in an instant. I'm going to use the positional component to set the position to 0 minus 10. This is what looked good. You can experiment with values. And here actually using the Z component is very important because we need to make sure that the sky, we need to set the Z value here. Here we set it to 1. So that because later on we're going to have a little cutscene that plays before the game starts where the dog is sniffing around. So the dog jumps into the bushes. And we need to set up set up the layer of the bushes, and yeah, so that we can put the dog behind it. So later on, it's going to be more obvious. So now let's load the sprite for this, again using the same logic. And now, if we look at the game results, now if we click, you can see that nicely the background with the trees and bushes is nicely displayed. You're going to notice again in this setup is that the UI is basically baked into the background containing the bushes and the trees. The reason for this is because when I went ahead and tried to find the duck hunt sprites, they were like that. So I modified them a bit, changing the colors, etc., to have something nicer, and I just left them baked, the UI baked into the image. Ideally, if you were in the control of your own asset creation, you would basically separate them and have the grass as its own layer, etc. You couldn't actually do that if you open up a pixel art editor. Just take the portion where the UI is and just separate that into its own layer, and then fill the rest with green for the background. Anyway, so now let's create our score UI, because you can see that in our background image there is the score UI but not the number itself. So let's add the number itself by creating a game object and storing it in a const called score. Using the add function, we're going to format the score again using the same thing, the positional component. The Z layer this time 2, because remember the background containing the trees and the bushes is on layer 1, so by having it on layer 2 for the score text, it's going to be displayed on top. Then the colors, we're going to set the color red for the text, and then actually it's not the correct position, so I modified the position, and we actually need to modify the color itself. So by just removing the color component, we can have the default color, which is white in Couplet. So now we have the score nicely formatted here. Now let's do the same for the round count. So the round count is where you see the red equal in the background image. It's where it's telling you on which round you are on. So here again, we create a game object with the round count stored in a constant called the round count, by the way. And then we use the text component, and here we just display 1 as the text. We again pass in the font options, text options we need. We use the positional component to set the position. We use the Z component to set the layer on which to display it. And finally, the color component to set up the color, which is going to be red. And then finally, it's the duck icons. So you can see in the original image, we have little ducks here that are now bluish because it's actually transparent. It's a cutout of ducks. So what we're going to do is just fill those cutout with white squares that we're going to be able to change the color of later on to red to demonstrate or show the player when they have successfully hit a duck. So to do so, we're going to create a constant which is going to hold a game object, and this game object is going to have the following position. And one new concept, first let's set a variable with the duck icon position x. So here you can notice that the constant we created is duck icons and not just duck icon. Because I'm going to introduce a new concept of Coplay. It's the fact that you can create children game object. So attach game objects to parents game object. So there's this parent-children relationship you can have with game objects. So here we have the duck icon position x, which is going to be a variable which we will use to offset each duck icon from each other. So here we create a for loop for 10 duck icons, and then for each of them we add a new game object. The way you create children game objects of a parent game object is you take that game object and use the add method on it. And that's how you create children game object of a game object. That's to be more precise, that's how you create a child. And then by doing this multiple times, you create children. So that way, we have a little rectangle with the width of 7 and a height of 9. Why this? Because this is what looked good, I guess. Fit well the cutout. Now the position is going to be using the duck icon pos x we used, that we're going to modify at every iteration of the loop, so that each duck icon is cut out square is put next to each other. And then we're going to use a tag using a template string, because we're going to use the tag, to identify each individual square that represents a duck icon, so we can really modify the color of the one we need specifically. And that's why I use a template string using the index, so to differentiate between each duck icon. And then after having created the child game object, we add 8 of offset in the x position, so that there is a gap between each duck icon. Now if we look at the results, you can see now that the ducks are white in the UI. Now for this to work out, just to show you, if in case it's not clear, I'm going to comment out the background containing the bushes and the trees, and you can see now what the game looks like without it. And you can see our rectangles representing the duck icons here that were just below the bushes. All right, so I hope this was clear. Now let's create our bullet UI mask. So again, if you look at the image, you can see that in the UI, you have the 3 bullets appearing. What we want to do is every time the user uses one of those 3 bullets, we're going to put a black rectangle that grows to hide 1, 2, or 3 bullets. Now again, this isn't something that you would do normally if you were to design your own game using your own assets. You would probably find something more modular than that. But just in our specific case, this is how I thought I would do it. But really, if we want to offer more than 3 bullets, we want maybe to be able to be flexible with the number of bullets, and that way it would be probably more appropriate to just have a single image of a bullet and then near it a number like 4 or 5 that you just update, and that would be the easiest way, I would say. But since we want to replicate, I guess, clone a old game, I guess we're gonna do it in a old-fashioned way. So here again, we create a game object called bullet UI mask. We create a rectangle, which initially has a width of 0 because we're gonna grow it gradually later on. So here again, position Z layer with the color being black by using 000 as our color here. So as you notice, you can use both RGB values or you can use hexadecimal values. So to be quick here, we know that black is just 3 zeros, and that's what I used here. Now let's create our game manager, which is going to be a very important part of the project. It's going to hold all the needed information regarding the game's state. And then later on, we're going to work on the functionality for the mask, the UI mask. The reason we're doing this is because we need the game manager to keep track of the number of bullets that are still left for the player. So here, let's create a function, call it make game manager, and it will return a game object. And it's going to use the state component. So we're going to use a concept called the state machine. It's a very important concept, and it is very useful for dealing with AI, so creating enemy AI, or dealing with animations, etc. It has so many applications. Here in our specific context, we're going to create a state machine with the default state being menu, and then we're going to have the cutscene round dash start, round dot end, dash end, sorry, hunt start, hunt end, duck hunted, duck escaped. These are all arbitrary names I have decided, which are going to act as our states. And the goal of a state machine is that for each of those states, you define custom logic you want to run when the game is in that state, when the game object is in that state. It's a nice way of organizing your code so that you can know or just really isolate and write the logic for that state in a specific place. So in terms of organization, it makes things much easier to understand as well. But I would say that to truly understand how it works, let's just actually do it, and then a concrete example, I guess, would go a long way to make you understand the concept. So one other thing that you can pass that isn't a component in the array of components of the add function when creating a game object is the ability to pass a JavaScript object, which you can use to define custom properties. So if you're familiar with object-oriented programming, it's basically your private variables, etc. for your class. So here we go, we create a bunch of properties. For example, we're going to create a isGamePaused property that we're going to use later to allow the player to pause the game at any moment. We're going to have the current score property, current round number, current hunt number. By the way, here I make a mistake. Number, the B should be in lowercase. I will later realize this mistake and I will correct it. But if you want, you can go ahead and correct it now so you don't do the mistake. Now the number of bullets left here can be is 3, and we're going to use that later on to keep track of the number of bullets. The number of ducks shot in the round initially is 0. The prey speed is the speed of the duck is initially at 100, and every time a round ends, we are going to increase the speed. Just to make things clearer, the difference between the hunt and a round is that the hunt is after every duck. So there's 10 hunts in a round. You have 10 chances, 10 duck you can shoot. So those are your hunts. And finally, we have the reset game state function that we're going to create, method. So here again, the way you create methods for your game object is just to create the function within the JavaScript object you pass. Here we're going to have one called reset game state. It takes as the first param this, which is a specific thing to TypeScript because this by default is not typed, and TypeScript is not going to be satisfied by that if you start using this. So that's why you need to create a first param called this and then type it. Here we're going to use the game object type offered by Kplay, so this should be imported at the top of the file, and then you can use this.current score and access the variables, the properties you defined on top here. And this function, this method, is really used to reset the game so that if the player wants to play again, they have this reset so that they don't they don't have false values and more bullets than they should have, etc. when they restart the game. And then finally, we just call this make game manager function we created, which acts as our constructor, and store it into a variable called a constant, called game manager. And then we're going to export game manager. So that means we only create this game manager once and use it in our game everywhere else. So now one thing we're going to do is create our cursor now. So create a constant called cursor, and then call the add function on that to create a game object, and then pass in the sprite called cursor, then of course load that sprite on top of our main.ts file. Once this is done, we can specify the anchor. So here it's very important to use the anchor component so that the cursor is drawn from the center of the game object, so it will correspond to the mouse. Otherwise it's going to look off. It's going to be positioned off, and it's going to be very noticeable. Then of course use the positional component here, but don't specify value. The reason for this is that we're going to set the position using the move to function that's going to come up later on, and you cannot have access to that function if you don't use the pause component here. So one thing I forgot to mention is that when you use those components offered by Kirby, it adds properties to your game object, and it adds functionality to it. So because you used certain game objects, certain components, then your resulting game object will have access to certain methods and certain properties that it would otherwise not have access to. That's why here I have no need to put to set the position of the cursor now, but I use the positional component still because I want to have access to the move to method later on my game object. And then finally we set the layer to being 3, so that it is displayed really on top of our game. Now let's look at the result. Or before that, let's actually write the logic for the cursor to follow our mouse. To do so, we're going to use an update loop. So a loop is something that is going to run every frame of our game, and it runs 60 times if your game runs at 60 frames per second. In Kirby, the way you set up a loop is by using the onUpdate Kirby function and passing to it a function that is going to be called at every frame. Just to make it simple, to explain it simply. So now here in that update loop, we're going to set the score text. So because we use the text component, the score game object can have access to the text property that we can modify. So we can now modify the text. And here we're going to modify the score here by setting the score text to the current score from the game manager. The reason we're doing this, and by the way, I said that we're going to use the onUpdate loop to make the cursor follow the mouse of the player, but we're also going to use this update loop to do everything else that we need to update. So the score text here is one example. Then we're going to use a switch case statement to know which width to give to the bullet UI mask, so we know how much it needs to cover to hide the bullets. So depending on how many bullets left, so if there's 3 bullets left, then the width of the bullet UI mask is going to be 0. Otherwise it's going to be 8. Otherwise, if there's only 1, then it's going to be 15, covering the whole portion of the UI I mentioned earlier on, displaying the bullets icon. And then so after we have that, to actually make the cursor move to the player, to the mouse of the player, to be at the same position as the mouse of the player and follow the mouse of the player, you can use the move to function and then pass to it the coordinates of the mouse. And the way you do that in Kirby is to use the mouse pause function. And because this is in an onUpdate loop, so at every frame it's going to get the updated position of the mouse and use that and move the cursor to it. So now if you look at the result, you can see that once I click start, I can have my cursor here that is following me around. Now finally, what we're going to do is we're going to have another onClick handler within the game scene. And this is just going to first have an if statement that is going to make sure that first the game manager is in the state hunt start. The reason we have this .state property is because we used the state component when creating the game manager, because remember it's a game object, and this offers us the state property that we can read to know in which state the game manager is. And here we're checking if the game manager state is in hunt starts, that means the hunt has started, and that the game manager is not paused. So this is a property that we have defined, so we can just access it here. And in that case, what we're going to do is we're going to first make sure that the game manager, the number of bullets is superior to 0. And then, so first of all, before we continue, this is the reason we're doing all of this is to play the gunshots. So here we're going to load the sound at the top of the file, call it gunshot, gun-shot, and then put the correct path. Now, if the number of bullets is superior to 0, we're going to play that sound, the gunshot sound, and we're going to set the gunshot. The way you play sound in Kplay is you use the Kplay function. You pass the name of the sound as the first param. The second param can be optionally options, like the volume that you want to use here, the volume, yeah. So here we set the volume to 0.5. Now, with that aside, what we're going to do is just, either way, we reduce the number of bullets. So this is the logic to play the shooting sound when the player shoots a bullet, when the hunt has started, because we don't want the player to be to waste their bullets outside of the hunt. So when the duck is either escaped and or hunted, and then you're waiting for the next hunt. So that's the logic for that here. We have here, and then yeah, so the logic to reduce the number of bullets, to shoot the bullets when it is appropriate by using an on-click. Alright, so now has come the time to actually write the logic for each of the states we have in our game manager. So this logic is going to be written in main.ts because we need to pull from other aspects of our game, and it's going to be the central place where we will be importing everything. So now what we're going to do is first create a constant, call it round start controller, and this is going to use the onStateEnter method of the game manager. Remember, this is available because we used the state component when creating the game manager game object. So because we used that component during the creation of this game object, we can have access to the onStateEnter method, which we can use to define what logic to run when a specific state is entered. Here we're going to use as the first param the name of the state we want to run the logic for, and it's going to be round dash start. And the second param is going to contain an anonymous function which will contain the logic we need to run when we enter that state. Later on, the reason I'm storing it into a constant, the reason I'm assigning it to a constant, the round start controller, is that for state machines, I have noticed that if you leave the scene, so go to another scene, the state machine still runs. So what we're going to do is we're going to keep track of all those controllers and then cancel them before leaving to another scene. This will come up later in the tutorial. So before we do anything, in our second param where we pass a function, let's make it async, and let's also add a first param in it. So it's going to be is first round, and it's going to be a boolean. This way we're going to be able to run different logic depending on if it's the first time the player or the game goes to that round start scene or not. And this is going to be relevant later on. So within that function, write a if statement where we first check if it is the first round, and if it isn't, we're going to increase the prey speed of the game that the game manager holds. Here we're going to do a plus 50 to the value so that the game will become progressively faster. Now, with this if statement, you can figure out that when we first enter the round start, when the player plays the game for the first time, we don't want to increase the speed of the ducks because it's the first time. And every time a round ends, then we increase the speed. That's why we have this logic to only increase the speed when it's not the first round. So all subsequent rounds, not runs. So now what we're going to do is load our assets. So what we're going to do is first display a message, I guess a UI, telling the player which round they are in. So this is the first thing they see when they should see when they enter this round start state. So to do this, we need to import our graphics and UI for that and sounds for that. So at the top of the main.ts file, use a load sound function call and pass to it the UI appear and the path to that sound, which is also in the sounds folder. Now we will, actually we don't really need to have an image for that since, actually yes, we have an image that we're going to load later on. So for now, just add a call to the play function from kplay. So by doing k.play and then the name UI-appear, this is the sound, a sound cue that we're going to play when the game enters the round start state. And as soon as we have this sound that we can play using the play function, we are going to increment the current round number. And once this is done, we are going to take our round count game object that we assigned to the round count constant and set some text to be the value of the current round number. Here I wrapped it up in a string, but really, like, you could do it without that because JavaScript is very flexible. You can just pass a number, etc., and it will convert it to a string. So yeah. Now what comes next is we're going to create the text box game object, which will display which round we're in. So we call the add method and pass to it the sprite component with the sprite text-box. Now we need to import that. If you look at your graphics folder in the public folder, you should see a file called text-box.png, and this is the box we're going to use for our text box UI that is going to display the round number. Now that this is imported, first let's make the game object render from the center, from its center, instead of the top left corner, using the anchor component and setting it up to use the center. And for the position, we're going to have the x coordinates follow the center of the canvas. As for the y coordinate, it's going to be the y coordinate of the center minus 50. So minus 50 means that it's going to be a bit at the top, because remember, the lower the value of y, the higher the value of y, the lower on the screen your game object is, because the Cartesian plane is kind of inverted, I would say. So the y-axis increases the further you go down. Finally, we put the Z layer using the Z component to 2 so that it appears on top of the background and the bushes and the trees, etc. Now we're going to add a child game object to that text box by just using the add method on that text box and passing to it an array of components. The component we're going to use is the text component, and then pass to it the text round with the text options we need, so the NES font and the size of 8. We are going to have the anchor set to center again for making things look nice. And the position is going to be 0, minus 10. And something to remember, I don't think I have mentioned this before. The position of a child game object is always relative to its parent. That means that 0 and minus 10 here are relative to whatever the current position of the parent is. So you take the parent's position and you add to it those two values, 0 and minus 10, on each axis. Now we're going to add a second child to that game object, that text box game object, and this time around it's going to be the current round number. Again, same logic. And here I'm I'm repeating the same text options over and over again. So you know what? Let's go to the constants.ts file and just create a font config constant that we're just gonna use once here, set once, and then import it in our main.ts and replace it everywhere else. So now that we have this done, let's add a call to the wait kplay function, which is going to wait 1 second. So we want the game to wait 1 second before the actual game starts. You can do that using kplay's wait function. There is two forms of that function: the async, the await version, async version, and the continuous, I would say the normal synchronous version, where here we're going to use the await version. Now what we're going to do is after 1 second elapse, we're going to destroy the text box game object because we want to basically remove that UI, and we're going to make the game manager state machine, which was created using the state component in game manager.ts, enter the hunt start state. And you can achieve this by calling the enter state method. And this is how you move from one state to another, is by calling this enter state method. Now let's define the logic for, well, actually, you know what? Let's first test this out. So just right below, outside of where we define the round start controller, call GameManager.enter state, with the round start state, which is the state we just defined here. And this will force the game to go into that state. Like if we look at the results, you're going to see that you have round 1 and then it disappears. And that's what we want. We have entered the other state. So now let's define the other states. So the round, not the round start, the round end controller, which again will follow the same logic, same structure. Let's have a to-do. Let's define them all, and then we'll fill each of them later on. So round end controller, and then hunt start controller, hunt end controller, duck hunted controller, and duck escaped controller. And that's basically it. So if I look back at GameManager.ts, you can see that yes, we have all the state covered. Now there's one we don't have. I think the cutscene, and the cutscene state, we do nothing with it. And the menu state is just the default. So when you define a state machine using the state component, you have to provide a default state and as the first param, and you also have to put it in the array containing the list of all possible states, which is accepted as the second param of the state component. Here we have the cutscene one. In the end, I don't think I ever used this, so it's not necessary to keep it. So you can comment it out or just leave it here. It won't do anything. So yeah, initially I thought I would use that state to run some logic, but in the end I didn't do it. So now has come the time to work on our entities, so the duck and the dog. So let's first work on the dog, which is going to first play a cutscene where the dog is sniffing around to find ducks, and then once a duck is detected, the dog will jump into the bushes. So to achieve this, let's first create a folder. This folder is going to be called entities, and let's have two files, dog.ts and duck.ts. So let's go to dog.ts. Let's first import our context, kplay context, using import k from kplay-ctx. Let's define our constructor, which is going to be a function that is going to be responsible for making the dog. Here I'm going to just call a function, call it make dog, and then have as the first param a position. Here I'm going to type it as a vector2. So vector2 is a type that you can import from kplay. It's essentially a data structure offered by kplay, which holds an x and y coordinate. and basically allows you to easily work with that. So since the typing is already offered by Coplay, let's use it here instead of inventing our own. Now we're going to return a call to the add function and an array of component. For now, let's keep it empty. We're gonna just write some other logic right before. So let's first create a const called sniffing sound. Here, what I'm gonna do is I'm going to call the Coplay function with the sound sniffing, which we haven't yet imported, and a volume. So the play function in Coplay allows you to play sound, as we have seen previously. It takes as the first param the name of the sound you want to play that has been imported using the load sound function. And as optionally a second param, you can specify values like the volume. Here I set the volume to 2 because that is what sounded good when testing the game. Now here what I'm going to do is I simply play the sound and immediately stop it. The reason I'm doing this is so that I can have the sound available at all times in that constant, assigned to that constant sniffing sound, so I can later on in my logic for the dog logic play it again. So it's kind of a way to load it in. So it's not the right terminology because to load a sound you use the load sound, but actually to keep it in standby, I would say I first assign it to a constant, and the only way you can do that is by playing it once, and that's why we play it and immediately stop it. So for the player, they will not hear anything. I'm going to do the same for the barking sound. So here's the same logic applies, and this time around we don't need to set the volume. The default volume of that audio was good, and we immediately stop it. And finally, the laughing sound, which again will have the same logic. So before we continue, let's go back to main.ts and import all of that sound. Let's first import the sprite for the dog because we're going to need that in a moment. So our dog here is in a sprite sheet, which is an image containing multiple frames. So if you look at it, it's a 4x3 image, so 4 frames per row and 3 frames per column. So now the way you're going to tell Coplay to divide this sprite sheet into different frames is by passing a third param to the load sprite function, which is optional, and then setting the slice x property and the slice y property. And as I mentioned, it is 4 frames per row. So slice x is going to be 4 and 3 frames per column, which is why slice y is set to 3. And then finally you have an anims property you need to define, and in that you can define your animations. So here I have an animation that I have decided to give it the key of search, and you pass to it an object, and that object contains various info or data regarding that animation. For example, our search animation starts from the frame 0. So what happens is that Coplay will slice your image into multiple frames, and then it will number them starting from 0, from left to right, top to bottom. That means that the first frame to the left is 0, then 1, 2, 3, and then you go down like that. Here, so that's why it's important here to specify the from property, so that we want the search animation to start from frame 0 to frame 3. So this will be the animation for the search, the frames for the search animation. And then we set the speed, which is the rate at which the animation plays. The more you increase this value, the faster the animation will play back. And then here we decide to make the animation loop indefinitely once it plays by setting the loop property to being true. So we do the same thing for the other animations, just it depends, the frame numbers will change depending on the animation, of course. And you might have noticed that some of the animations only have 1 frame, and when you have only a single frame that you want for that animation, you can just give the number of that frame immediately instead of passing an object to the key you want. Alright, so now that our animations are done, are set up, We actually have to import the audio, but before that, let's have our game object for the dog set up. So in our array passed to the add function, let's use the sprite component and load the display the dog sprite. Let's set the position by passing the position we in the make dog function to the pause component. And then let's have a state machine specifically for that dog, which will allow us to define its logic and its AI basically. So this is how I was able to have this little cutscene in the beginning of the game where the dog first goes around and sniffs until the dog is detected. And once the dog is detected, the dog jumps and etc. So that's why the state we're going to use is the search state, which is going to be our default state. And then in our array, remember, you need to provide all the possible states. So you have to provide search again. And then here I decided on the sniff, detect, jump states and drop state, because the dog jumps in the bushes and then drops behind them. And the layer, we need to set the layer initially to 2. And this, because we use the Z layer component in our game object, we're going to be able to modify its value later on. And this is how we can achieve that the dog is first in the front on layer 2, and then it's going to go behind the bushes by changing the layer to layer 0 or 1. And then finally we pass an object to set some properties and our methods for our dog. So here I set the speed to 15. I create a method called search for ducks, which is going to run initially at the beginning of the game before the game actually starts. And this will be responsible for having the dog move around and then sniffing and detecting and then jumping and dropping behind the bushes. So in this function, again, we need to type this. This is a TypeScript thing, as I have explained previously. It will be actually removed when it is compiled to JavaScript. So here, let's declare a variable called number of sniffs. The reason we're doing that is that depending on how many sniffs the player is going to hear, we're going to do something different with the dog. So here, let's define our states logic for each of our states we just defined. So for the search state, we're going to first play the search animation. So this is something that might confuse you, because in kplay, k.play is the function from kplay to play audio sound. But when using the play method on the game object is to play an animation. Here we are playing the search animation and not playing a search sound. Something to keep in mind. You need to be very careful about this, because sometimes you can easily be mistaken and then get confused. So now let's load our even I got confused. I initially wanted to load the search sound, but it's not, there's no search sound, so it's a sprite. Anyway, let's load our sounds that we had: sniffing, barking, and etc. But first, let's do it with a sniffing sound. Now let's go back to our search state logic. Here we're gonna use the wait function. This time around, we don't need to use the async version. Let's just use the synchronous version. So just to demonstrate, you can use the synchronous version by doing k.wait and then pass as the first param the number of seconds you want to wait, and then the second param is going to be the function that is going to run. If you were to use the asynchronous version that uses a wait, what you have to do is just there's only one param to pass, which is the time to wait, and then once the time has elapsed, whatever is below the call to wait will run. So here we will enter our sniff state after 2 seconds. So first the dog searches while moving, and then he's going to sniff first, and then, okay, no ducks were found. Sniff again, no dogs were found, and then I think a third time, and then, a duck was detected, etc. So that's why we do this. Now let's define what happens every frame when the dog is in the search state. So you might be familiar with the onState enter, but this is onState update method, which allows you to have more granular control and run a function every frame while you are in a specific state. So here again, this is used to make the dog move from left to right, and the way you move things in Play is by using the move method on the game object. You pass to it two params. The first one is the rate of movement to the x in the x-axis, and then the rate of movement on the y-axis. So here I pass the speed on the first param, which means that the dog will move only horizontally and not vertically. That's why I set the second param to 0. Now let's define the sniff state, the logic for when we enter the sniff state. Here again, I'm going to increment the number of sniffs, variable we had created earlier on. Then I'm going to play the sniff animation on my dog. And this is what, yeah, so I made another mistake. By the way, it's not sniff, it's sniffing for the sound. And there is this actual sniff animation. So that's why, let's load the barking sound now and the final one, which is the laughing sound as well. Now, for the sniff animation, we don't have to define anything because it's already included in when we loaded the dog sprite sheet. Here we play the sniffing sound, we wait 2 seconds, and then we stop the sniffing sound, and we first check if the number of sniffs is equal to 2. If it's the case, that means we enter the detect state, and that means that the dog has detected a duck. This is all a scripted event, like a cutscene. So that's why it is hard-coded to 2 sniffs. And then we return early. By doing this, you make sure to prevent the logic that comes after to run. And this can occur where you enter a detect state and then the code still runs in the on-state enter of the sniff state, and you will find yourself in the search state instead. So be careful with that, with state machines in Play. So in the case it's not, the number of sniffs is not equal to 2, we enter back into the search state, and this will rerun the logic for sniffs, and then we'll hear the sound again, etc. Now for the detect state, we again use the onState enter function, and then we play the barking sound. We also play the detect animation, then we wait 1 second, we stop the barking sound, and then we will enter the jump state. For the dog will enter the jump state. And then finally we define the jump state, and we again play the barking sound again. By the way, the reason I'm doing this in a specific order, etc., is just to replicate the original Duck Hunt, which had an exact similar cutscene at the beginning of the game. And then we play the jump animation, and we wait 0.5 seconds, which is what looked good. We stop the barking sound. We then use the use method on the game object to change the Z layer. So I'm not sure, but I think the reason I did this is because you cannot actually change the Z layer. Otherwise, try doing this.z equal and then change the value. If doing this works, that means you should do the way I just said instead of using the use method here. The use method here is when you want to add components after the fact, after having created game objects. You use the use method. So for example, you created a game object with 4 components, then later on you need some other ones, then you use the use method here to add new ones. And then finally we enter the state, the drop state, and this in this we don't need to have an onState enter function to run here. We only need to have the onState update because we want to move the dog every frame downwards so that it looks like actually first we need to make the dog look like it's jumping and then go down. So the way we do this is first we move the dog using the speed on the x-axis to 100 and then the y-axis minus 50. This will make the dog move to the right and up. And this gives the impression that the dog is jumping. Then as soon as we enter the drop state, so this for the drop state we actually need to have an onState enter. And by the way, we actually did use a onState enter definition for the jump sound. Sorry, I forgot about it. And so now in the onState enter for the drop state, we're going to have a sync function and use a tween. So a tween allows us to gradually change a value from a specific value, original value, to a target value in a certain duration using a certain easing function, which is a rate of change, which can make your game look really good if you use them well, because you can have all kinds of effects like an ease out bounce, etc. And the way the tween function works in Kplay is that it takes as the 4 params. The first param is the original value. Here we're gonna pass the y position of the dog. Then the target value, here we want the dog to be at y position equal to 125. This is what looked good while testing the game. The duration, let's do this in 0.5 seconds. And you need to pass actually it's 5 params, not 4. You need to pass a function that takes care of modifying the value. So here this function is called at a rate that follows the easing function we're going to pass in the 5th param. So here we just take the new y, or the new value, which is passed to that function we passed as the 4th param, and set it up to be the new value of y. And then finally, for the easing functions, you can access all of the possible easings offered by Kplay by using k.easings and then dot, the name of the easing. So let's use the simplest one, the linear one. So those follow math functions, in case you're wondering. Now, what we're going to do is have our game manager, and this, make sure to import it, by the way. And the reason we want this is to make the game manager enter into the round start state, sorry, not scene. That way, we make the cutscene end and immediately go to inform the game manager that, okay, now the game can start, the round can start. And it's the first time we enter that round. That's why the second param is set to true, because in the game manager, we had you remember we had a param that we created to make sure to have different logic depending on if it's the first time or not, and this was defined in main.ts. So now let's write our second method for our dog, which is going to be a slide up and down method. This will allow the dog to slide up. So this occurs when the dog, when you, for example, shoot a duck, or even when you fail, what will happen is that the duck will either flee or get shot and then fall to the ground. And then after that, the dog will slide up from the bushes. And depending on if you were successful, then he will rise with the duck in his hand, the dead duck in his hand. While if you failed, then the dog will rise up and laugh at you. This was something that was in the original Duck Hunt game. Here again, to do this, we use a tween. And again, like I mentioned, it's the same principle. We first slide up with the first tween, where the position, the target, the original value, the target value, the duration, the function that actually changes the value, and then the easing function that will determine the rate of change. Then we have an await. So the reason we have an await here, we use the await variation of the tween, because there is a synchronous version, is because we want the first tween to run, make sure that the dog rises up, and then wait 1 second using kwait, and then make the dog rise down. So go down, not rise down, go down. Again, using the same logic. So now that we have that, let's write one other method. And this one is to catch the fallen duck. This will just play the catch animation, which is just a single frame where the dog has the duck in his hands. And that's it. And let's load our sounds we need. So the successful -hunt sound, if you look in your public folder, you should see it. I'll load that in main.ts, then play that sound, and then once we play this, we will call the slide up and down method we just created, and you can have access to it by using this dot slide up and down. And then finally, we're going to make our game manager enter the hunt end state. As I explained earlier on, a hunt is a single try, while a round is 10 tries. So here, after having successfully hunted a single duck, we can consider the hunt to have ended. And then the other final method, sorry, there was one more, is the mock player. And again, this will just play this sound, the laughing sound, sorry, that's the proper pronunciation, I guess. And then call the slide up and down function, and then also enter the hunt end. So depending on which function we call, the dog will display different animations, which again, depending on the situation. And then I forgot to add in the mock player, play the mock sound, not mock sound, the mock animation where the dog is laughing. And that's it. And now we can go to main.ts and create a constant that we will assign to it the dog game object. So call it dog, and then make sure to, of course, import makeDog at the top of main.ts. Then pass to the makeDog function a vector2. You can create a vector2 on the fly using the vec2 capital A function, which takes in two params, or either the x and y coordinate. So here we're gonna have 0 for the y coordinate, the x coordinate, sorry, and the center of the canvas as the y coordinate. Then we're gonna call the search for ducks method immediately after having called our makeDog function. And that's it. So now before we test things out, let's add the logic for to cancel all the controllers we have here when the player leaves the scene. So that's why I'm going to use the onScene leave capital A function, and then have our round start controller, round end controller, hunt start controller, hunt end controller, duck hunted controller, duck escaped controller, and the game manager reset game state function. So all the controller are going to get canceled using the cancel method, which is offered by Kplay. And that's it. That's how we reset our game. So for example, when you go to the game over screen and then come back, everything's going to be fresh, I guess. Now, if we look at the result of that, so let's click, we have our dog that sniffs around multiple times. And then detects and then jumps, and then we have the round 1. And that's it for now. We can shoot the bullets, but nothing more. So now that we have completed the logic for the dog, let's do the same for the ducks, or the duck. So in our entities folder in duck.ts, let's start writing the logic for the ducks. So first of all, I will first import the K, or the CarPlay context, and then create a constructor function called makeDuck. And this is, again, going to have mostly the same logic, but it's going to actually take different params. Actually, the logic is a bit different from the dog, to be more precise. We're going to have two params. The first one is going to be the duck ID. This is a way for us to know which duck is which amongst the 10 ones in the run. So the 10 ducks. We want to be able to differentiate between them so that when we shoot one, we can know for which duck icon to color red in the UI. So that's why we're going to pass the duck ID as a string. And the speed here, we're going to pass to the makeDuck constructor here, so that we can modify the speed of the duck in further rounds, so to make the duck faster. So first of all, let's have a constant containing the starting positions, and it's going to be an array which is going to contain various positions from which we can launch the duck from the bushes, so that it adds a bit of variety to our game. Then we're going to return, of course, a call to the add_a function to create the game object with an empty array for now. Now, in our starting position, every one of those positions is going to be a vector2, and let's write them out here. So here are 3 positions I have decided to add You could tweak those values if you want after having followed these tutorials. Yeah, so that's arbitrary values that looked good. And you also need to make sure that it looks like the duck is coming from the bushes out to the sky. So now what we're gonna do is have another constant. This time around it's an array again, but for fly directions. We're gonna have 3 vector2s determining directions from which the duck will go towards, in which direction they're gonna fly. So here we're gonna have normalized vectors. So this is something a bit of a math, you need a bit of math knowledge here. So we have -1, -1 on the X and Y axis. Here you need to see them as angles, I guess, from which the duck will follow. And you don't really need to know your math related to vectors here, but it's helpful to learn a bit more about linear algebra. Anyway, so let's have our fly directions here. And now we're going to have another constant, and it's going to be the chosen position index. So chosen pos index. And this is going to randomly select from the starting pos array a single position we're going to use for that duck. So here we use the randy Kepler function for that. A random stands for random integer. And we pass to it the array, the length of the array, and it's going to give us a value between 0 and the length. And of course, it's going to exclude the outer bound, I think. I hope so, if I remember correctly, so that we can never have an out of bound index. And then we're going to do the same for the chosen fly direction index, but for the fly directions array. Here we're going to have our duck sprite loaded here with a default animation. So before we proceed on, let's go back to main.ts. And in main.ts, let's load our duck sprite. Here again, I do it quickly. And again, it's the same principles. You can use a string for the key, by the way. You're not constrained to a single word for each of your animations. So yeah, that's that. Now, if we go back to our duck.ts file, and here we set the default animation to flight dash side. We set here an area component. So the area component is a very, I would say, crucial component when working with Kepler. It creates an automatic hitbox for your game object, which allows you to detect collisions. Very important. And here, not only does it does this automatically, the area component, but you can also optionally pass to it a specific shape you want for that hitbox. And this is what we're going to do here. I'm going to pass a rectangle by using the rect constructor from Kepler and create a rectangle, which takes as the first param its position relative to the game object that uses that shape, that hitbox. Here we just pass a vector2 with the value 0 in it, and it's going to replicate it for both the X and Y axis. So basically what we're saying is that we want the rectangle shape hitbox to be at the same position as the game object itself. Then for the second and third params, we set the width and the height of the rectangle. Now we use the body component right after. The body component is another crucial component in Kepler. It allows you to make your game object susceptible to gravity, and it also allows you to have access to methods that we're going to need here. In this game, I don't think we use gravity at all. We just move programmatically the objects, the ducks, etc. But we still need to use the body component, if I remember correctly, because we need access to certain methods that are only offered when you use the body component. And finally, we have the anchor component to center the game object in its center rather than its top left corner. And finally, the position, we set the position by taking the starting pos array and passing the chosen pos index. And finally, we're going to have also a state machine for the duck. which is going to contain 3 states: the fly, shot, and fall states. And finally, a timer component is going to be used, which will allow us to have timer methods on that game object. And finally, again, I say finally a lot, but I think that's the true finally, I guess. We're going to have the off-screen component, and this off-screen component is going to destroy the duck when it leaves the screen to free up resources. It takes optionally, you can pass to it a game object, not a game object, a JavaScript object to tell it how to behave. So here we set the destroy to true. That means that when the game object is off screen, you're gonna destroy it and not just pause it or something like that. And you're gonna destroy it when the distance outside of the visible screen, the canvas that is visible by the player, is 100 units. Now we're gonna add an object here to define our properties and methods. So the fly timer here is going to be used to count the duration of time in which the duck is trying to avoid the hunter, the player basically. Once this time is elapsed, we're going to, so that's the second property, time before escape. After 5 seconds, we're going to make the duck leave the screen. That means the player has failed that hunt. The duck ID can be taken straight up from the params of the makeDuck function. This is a JavaScript feature, by the way, so that you don't have to repeat duck ID colon duck ID. And then for the fly direction, here we're going to set it initially to null, and then we will set it up later on in our methods. As for the speed, same as with the duck ID, we pass it directly from the makeDuck param, speed param. Quacking sound, flapping sound, etc. are sounds that we're going to add later on. So now let's create our first method, which is going to be the setBehavior method. And in that, we're going to set the fly direction to be the fly direction array, and then the chosen fly direction index. And then here we're going to make the duck face the correct direction. The way we do this is if the x component of the fly direction vector is inferior to 0, and then we will flip the image like a mirror on the x-axis, and that way, that way the duck will face to the left to the left, because by default I think the sprites face to the right. Now we're going to play the quacking sound with a specific value. Let's import it in our main.ts file. We're going to do the same for the flapping sound. And then here we're going to play the flapping sound, which is basically the duck flapping its wings. And then we're going to have special options here. We're going to set the loop to true. So you have two options. Either you do this, so setting the speed and the loop here. You can do it when you define the, actually, never mind. This is a sound. Again, sometimes I confuse myself because the API for dealing with animations and the API for dealing with sound is very similar syntax-wise. Here we're repeating the flapping sound indefinitely at a speed of 2. So we are making the sound plate at twice its speed, normal speed. Here again, we're gonna use the onState update, onState enter, etc. to define the various logic we need for each of our states. So here we go. Now, of course, we need to import our game manager. And here we're gonna have an onClick, which is onClick can both be a function from CoPlay and a method on a game object. So if your game object uses the area component, you can use the onClick method. So here you pass to it a function that is going to run every time the player clicks on the game object. Here we check if the number of bullets is inferior to 0. If that's the case, we're gonna return early, because that means we don't want to make, so for example, if I no longer have any bullets and I try to shoot the duck by placing my cursor on the duck, then we need to actually check that there are bullets left. Otherwise, we're gonna make the duck shot, even though it shouldn't be the case. So that's why we return early and do not run the logic needed for when the duck is actually shot. So here we're gonna if it's not the case, that means we have bullets. We're going to increase the current score by 100. We're gonna play the what's the sound? The shot sound. Actually, no, we're gonna play the animation of the duck being shot, which is also named shot. And then we're gonna enter the shot state. Now we're gonna get the sky game object, and the way you can do this in a very handy way is to use the play get function, which allows you to get a game object or all game objects that have a certain tag. So it gives you all possible game objects that have the tag sky. If you remember, at the beginning of the project, we defined this in main.ds when we created the sky game object. So here, by calling k.get sky and then passing the taking only the first index, because there should be only one, because remember it returns an array, then we can get our sky game object. And then we're going to have a loop, and the reason we can use the loop method on the game object is because we used the timer component. You could have decided to use the play loop function instead. I think there is one. The reason we want the loop as a method of the game object rather than using the loop function from play is because we want to destroy this logic, cancel this logic automatically when the duck leaves the screen. It's going to do this for us. That means we don't have to worry about keeping track of our loop logic here and making sure to free it when the duck is gone, for example. So that's why I used the timer component and use the loop method here. So now in this loop, we put as the first param the frequency of that loop. So every 1 second, we're going to run the function passed as the second param. So here what we do is we just increment the fly timer property, custom property we created by 1. Now if the fly timer is equal to the time before escape, that means that the time has elapsed and now it's time for the duck to flee. Then we're going to change the color of the sky. And to do this, we're going to use the sky.color and then set the color using hexadecimal. And the way you do this, if you're not using RGB, is to use the color constructor and from hex method. And then here we're going to go back to our constant.ts file and just write the hexadecimal code for the beige color and then use it here. Remember to import the colors constant at the top of the duck.ts file. Then finally, we're going to have a method called on exit screen, which again, this method is available because we use the off-screen component when creating the duck game object. It takes as a param a function, and that function will run as soon as the duck exit the screen. And what we're doing in that function is just to stop the quacking sound and the flapping sound as well, and to change the sky back to the color, the original blue color. Now you might be wondering, why did we change the sky color in the first place? That's something in the original Duck Hunt game. When the duck is now escaping, so after some time has elapsed, the sky will change colors for a while and then the duck will escape and then the hunt was basically failed. Now we're also going to reset the number of bullets for the next hunt, because remember there is 10 hunts in a single round. So let's set up back the number of bullets and we're going to enter the duck escaped state. So now let's write the logic for the shot state. So here we have the game manager and we're gonna increment the number of ducks shot in round, and we're gonna play the shot animation of the duck. Then we're going to Actually, we don't need to play the shot animation because we do this earlier, so we don't need that. We're going to stop the quacking sound, we're going to stop the flapping sound, and we're going to wait 0.2 seconds, and remember to make this async, before entering the false state. Now, before doing the logic for the false state, let's do it for the fly state. So every frame, that's why we use an onState update, we're going to first check that the fly timer is inferior to the time before escape and that the position on the X coordinate of the duck is superior to the width of the screen plus a small offset of 10, and that the position is also inferior to -10. The reason for that is to make sure that the duck is not so the reason for this is that when the duck is near the is outside of the screen with a certain little gap, we're gonna make the duck come back, bounce back, a bit like the DVD player logo that you see, the famous DVD player logo that bounces off the screen and comes back. This is the same logic we do here. So here we're just gonna set the fly direction X coordinate to X component, sorry, to be the inverse, and then for the Y we're gonna just have the same value, and this is going to achieve the DVD player kind of logo bouncing off effect. Also, we just gonna reverse the image, the sprite of the duck as well, to give it the mirror or the mirroring effect so that it goes into the other direction, and you can achieve this without needing to know if the duck is currently flipped or not by just setting the flip X property of the duck to be the inverse by using the bank sign before the this.flip X. And then finally, we're gonna get the current animation, assign it to a constant by using the getCurAnim function method and getting the name. And if the name is equal to flight side, then we're gonna change the value to flight diagonal, and otherwise we're gonna make it flight side. The reason for this is that when it bounces back, it's going to fly in a diagonal fashion. And then finally we play the current animation. So yeah, so we get the current animation depending on if the current animation is the animation that is already currently playing is flight side. We're gonna change it to flight diagonal. Otherwise, we're gonna keep it to flight side. That's what we're doing here. And then finally we play that animation by passing the current anim to the play method. Now for the Y position, so this is horizontally. Now vertically, we're gonna do something that's very similar. And again, but just for the other, the other direction. Now, if we now for actually moving, so now that we have set the new fly direction we want in either cases, either on the horizontal or vertical axis, what we're going to do is to actually move. Since we're in an onState update, so every frame this will run, we're going to use the move method from Kplay, which I think is there because we use the body component. Try the same logic without try after this tutorial removing the body component from the duck and try to confirm if it was actually needed, because I might have added it without realizing if it is actually needed. Anyway, so to move the duck in the direction we want, we're gonna pass the direction to the move function. This is another way of using it, and basically it's a vector 2. And now we're gonna scale it according to the speed. So remember, the fly directions were -1, 1. Basically they were normalized, so the value was only between 0 and 1, and either negative or positive. By using the scale function here, our method, we can scale that value to correspond to the speed. And I think, again, if fly direction is a vector 2, you can skip on wrapping it inside of another vector 2. That might have been a mistake on my part as well. So now for the false state, when we enter on state enter, sorry, here we're gonna make the false sound play, and remember to import that sound in main.ts. and then play the fall animation. And then for each frame, using onStateUpdate for the fall state, we're going to move the duck that is now falling only in the vertical direction, I guess, vertically only, setting the first param to 0 on the x-axis, and this.speed for the y-axis, so that the duck will fall. And then finally, if the position of the duck on the y-axis is superior to the height -10, then we can be sure that the duck has fallen to the ground, and now we can play the impact sound. So before doing that, of course, remember to import that sound in main.ts. And then once the sound is imported, play it and make the first make the fall sound stop, and then play the impact sound. Then destroy the game object by using the destroy Kepler function and passing into it this, because this is the game object itself, the duck game object. And then finally change the sky color to being what color we need here, to being blue, in case it weren't blue. So in case where the duck is trying to escape, is starting to escape, but you shoot it, and then we need to actually change the sky back to blue. Make sure that the sky is back to blue regardless anyway. And then finally, we're going to get the duck icon specific to that duck. That's why we use the duck ID here. And remember, when you use the get function, so if you want to get a game object that is a child of another game object, and you want to get it using the get function, you need to set the second param with an object, a JavaScript object that has the property recursive true, so that it is going to search for game objects even within other game objects, so the children of game objects. And then since we expect only one duck icon to have the specific tag here, we're gonna just simply need to get the first index, the first element, and that is going to be our duck icon. Now, of course, if a duck icon is defined, make sure this for TypeScript to shut up, we're gonna have the duck icon color and set it to red using the, again, from hex method. We wait 1 second, and then we enter the duck hunted state from our game manager. Now let's write the logic for the hunt start so that we can actually see our ducks. So here I'm gonna use the game manager and then set the current hunt number, increase the current hunt number. As soon as a hunt start, we do this. Here again, I made the mistake to call the property current hunt number with NB being capital letters, but actually I correct this later on by having the N capital and the B not capital, regular basically. And this isn't a big deal, but if you were following along, just make sure to have the exact same thing. Otherwise, you're creating a new property with that value, different name, and this could cause bugs and you might not know why. Now let's call our duck. Let's create our first duck here by calling the makeDuck function and assigning it to the duck constant. Here again, we're gonna have the ID, which is going to correspond to the current hunt number -1. And now, because the duck icons are numbered from 0 to 9, that way we can have the duck icon with the duck with the ID of 0 is going to correspond to the first duck icon. That's why it is -1 here. And then the prey speed from the game manager, we pass it here as well, so that in further rounds, when we re-enter the hunt start state, the prey speed value could change, and that's how we make the duck go faster. And then we call the setBehavior method. And now if we look at our results, so we have our little cutscene in the beginning, and then once the dog will jump, round 1 starts, and then there is, and nothing happens for some reason. There is an issue. So in the next part of this tutorial, we will fix this, this issue. All right, so the error that I made was at line 65 in duck.ts. The issue was that the scale function method is called within the vector, the fly direction. It's a method on the fly direction vector. So just yeah, do what you see on the screen. And by the way, I think that fly direction is a vector, so you might not need to wrap it using vector2, but I'm not sure. So now we can look at the result. If I click, we have our cutscene. Then, yeah, let's wait for the cutscene to to end. Then the dog will jump, and then round 1 starts, and then we have finally the duck that comes out, and then we can try to shoot the duck, and the duck fell, and now we, for some reason, the dog is not rising up, and that's an issue. So we need to fix that, or actually I think we haven't written the logic for that. So in hunt end, I think that's what we're going to do. Yeah, in hunt end, create a constant called best score, and we'll just get the best score from the local storage. And then if the best score is inferior to the current score, but before that, wrap the get data call to be in with the number constructor, so that we make sure that the best score is a number. Because remember, here get data can return either null or none or something, or the data we want, so it's not specified. So by making sure that we have a number, we're pretty much sure that we're gonna get a number, but just so that TypeScript shuts up, we need to do this. So now if the best score is inferior to the current score, we set the best score to being the current score that is available in the game manager. Now that's after a hunt end. Now, so that means that every time we end a hunt, we update the best score. In case so we update it so that at the end of the round, we will have the up-to-date best score. Now, if the game manager current hunt number, again, the same issue we had with number, it should be capital N, but non-capital B, is inferior or equal to 9, that means that we can enter into another hunt by going to the hunt start state. The reason we're doing this is because if we were to have the current hunt number to being superior to 9, that means that we have actually exceeded the number of hunts in our round, which is supposed to be 10. So we return early because by default, if none of these if statements are true, we will just have our game manager a current hunt number, and this is where I actually fixed the issue. We're going to set it to 0, and then we're going to enter the so first I need to modify everywhere else where I used current hunt number wrongly with the wrong syntax. But after that, we can go to the round end. We're gonna first write the logic for the duck hunted state, and then we will write the rest of it. So first of all, for the duck hunted state, we set the numbers of bullets left to being 3, and then we play the catch fallen duck function method that we had for our dog that we defined in our dog logic. Then we will, in our duck escaped state handler for our game manager, we're going to have the function mock player, the method mock player from the dog run here. And that's it. So now by adding those two things, we can go and test our game again. So now if I click to starts, and now we have our cutscene again. So yeah, this might be, I should have probably written some logic to skip the cutscene, but anyway, that's too late. You can do this as an exercise. So we shoot the duck, and then the dog will appear on top, and we can see that the duck icon has become red. Now again, if the duck escapes, you see that the sky changed the color and that the dog laughed at you. And here we go. We have, I think, the full gameplay. You can see that the score is updating, and the number of bullets, the mask is also hiding the bullets icon to basically tell you that there's only like 2 bullets left or 1 bullet left, etc. So now let's try to complete a round. We have enough to pass to the next round. So let's just, wait. Just to see the bouncing in action. And the dog laughing at you. And now nothing happens. That's, I think, because we haven't written the logic for when the round ends. So for round end, if you go back to the round end controller definition in main.ts, we're gonna first have an if statement where we need to check if the number of ducks shot in the round is inferior to 6. If that's the case, that means that the player has failed the requirement where they need to have at least shot successfully 6 ducks before moving to the next round, if to move to the next round. So here we go to the game-over scene that we're gonna define later on. We have defined it, but we're gonna fill the logic for it later on, and we return early. So if that if statement is not true, that means we're gonna first check if the number of ducks shot in the round is equal to 10. And we do this to give the player a bonus. So we're gonna increase the current score by 500. That's a bonus. I think it was like that in the original Duck Hunt game. Finally, in either cases, regardless of if the number of ducks shot in the round is 10 or not, we're gonna reset the number of ducks shot in round to 0. And for each of the duck icons, we're gonna color them back to being white by passing a color component with the RGB values 255 on each of the color channels, which corresponds to white. Then we're going to enter the round start state again. And now if I test the game again, and I'm just gonna fast forward a bit, and then you can see I'm just gonna fast forward to the point where we are in the last, here, and then round 2, and then you can see that we have our bullets back and that the score is keeps increasing and that the R equal is now 2 instead of 1. So now we can say that we have a fully functioning gameplay of the game. Now there are a little bit of finishing touches we need to add, and as you can see that the ducks in the round 2 are faster than round 1. If I skip around and go to a further round, so by the way, one thing I forgot to mention is let's activate debug mode here with the F1 key on Windows and Fn plus F1 on Mac OS. You can see that there is a box drawn where the duck is, and this is its hit box, sorry. So now, you can see how handy it is to have a debug mode. We will have to deactivate it later on before going to production. And you know what? Let's stop here. So now we're gonna go to the game over definition of the scene, and we're going to add a couple of before that, let's add the sound, the forest ambience sound. So there is this sound called forest-ambience in the public folder, in the sounds folder. Let's import it here and play it in main.ts. So here I set the volume to 0.01 with a loop being true. So that's what you need to do if you want a sound to repeat itself even after it ends. Of course, import it with the load sound function. And this shouldn't be new here, this concept of importing sounds. And now in the on-scene leave, make sure to add this so that we can't, we stop the sound when we leave the scene. Otherwise, the sound will continue to play even if you leave and go to the game over scene. So we don't want that. This is for sounds that loop. If your sound were not looping, you wouldn't need to have this. You need to make this call. So now if I play our game, you can hear you can barely hear it, but that's because I made a mistake and the volume should be set to 0.1 and not 0.01. Otherwise, you can basically not hear it. So if I do it, if I set it up back to 0.1, and now it should, yeah, it should be able to hear it. And now we're ready to work on the game over scene. And for the game over scene, it's just a game object that's going to be a rectangle that will take the whole width and height of our canvas, and it's going to be of a black color. And we're going to have some text, and it's going to, by the way, since we I think we did this, yeah, since the background, the page itself is black, you wouldn't need to add this game object if you set the background property in the CapLay context. But if you didn't, you would need to create a rectangular game object to act as your background. So this first line, you can skip it if you use the background property in the CapLay context, where you define the CapLay context. Now here I'm having some text with game over using the font config, and make sure to import it, etc. And then this is nothing new. Nothing new. And then we wait 2 seconds before before going to the main menu, so that the player can play again and they can see their top score, of course. And that's it. That's the game. And now if we try to play it, yeah, so I think we did it. Yeah, so the game is fully functional now. The only thing left, and another feature I wanted to add, is the ability to pause the game at any moment. This isn't really necessary for this game, but I wanted to teach you this because it's not something you would come across very easily. And in CapLay, to make something pause, let's go to main.ts and use the onKey press CapLay function and pass to it a function with a param key, and then this will give you the key being pressed. And if the key being pressed is P, that I decided that way, I'm going to get the tree root in CapLay. You can do this by doing k.getTreeRoot and take the paused property and set it to the reverse of it. That will allow you to, if the tree root was paused, it's going to unpause it, and if it wasn't paused, it's going to pause it. And now we're going to have another if statement within, and if the get tree root is paused, what we're going to do is we're going to set it in our game manager here so that we can keep track of when things are paused, etc. Now, the reason we need to set the isGamePaused property of our game manager game object is because this is what is used outside in our game for the ducks, the dog, etc. when it comes to their movement, etc. So that means that if this is set to true, it will stop the I think the movement for those game objects. It will stop certain logic from taking place. Now there's a bit of code that is a hack. So we need to TS ignore this because there's this global variable called audio CTX or audio context. And I really don't know from where this comes from, how to type it, but it is something that is globally available in your browser and allows us to suspend our audio context. The reason we need to do this is that for now, if you were to not have this code, what would happen is that the sound of the game would continue to play despite the game being paused. And of course, we don't want that. So that's why we use it here. But since I really don't know how to type it and I haven't found any info on this, I will just ignore whatever TypeScript wants here, and by placing a comment right on top called @ts-ignore. Now, to make things more complete, let's display a game object at the top left corner that says the paused, so that the player knows that the game is paused and hasn't just frozen. To do this, let's create a game object with a paused text using our font config with the position 5.5 and a Z layer being 3, and let's give it a tag of paused dash text, because we're gonna write the logic to remove that game object when the game is no longer paused. So here we're going to have an else statement, which I'm going to remove in an instant and show you how to to use just a return statement instead of having an if-else. But just for the sake of explaining, here I'm going to set the is game paused to false. I'm going to again ignore the audio context here to resume it using the resume method. I'm going to get the paused text using the get function, couplet function, and then I'm going to destroy it. So now this should work, but now I'm going to show you that you can just achieve the same thing by just having an early return statement in the if statement and then remove the else. So now things should work, and I think it's time to test it out. So let's open up our game, and when I click start and I click P, it is paused, and now I can pause and unpause, etc. And that's basically the game. Everything has been implemented, and you have a fully working Duck Hunt clone. And actually, there is one thing missing. Yeah, just one thing to remember. In our duck.ts file, I remember commenting out the display shot, playing the shot sound in the shot state. This was not necessary because we played it elsewhere, so you can remove it. And now has come the time to show you how to deploy this. So open up your terminal and run the command npm run build. Once you do this, it's going to create a dist folder. And one thing I forgot to, and then before doing that, to test that it works, do npm run preview and go to the local host, and then you can see if your game is working or not. Now, before doing that, create a vite config.ts file. And this is just to make sure that it is going to work on websites like itch.io, etc. Import the define config from vite, which is the build tool we've been using, and then export default a define config and call the define config thing and set the base as a /. This is to make sure that the assets are going to reload in the correct place, etc. So now if you run npm run build and then npm run preview and then open up the game, everything should work. So what you need to do to publish this game is you take your dist folder, you zip it as a zip file, and then you publish it, you upload it to websites like itch.io, etc. So that's the tutorial. That's it. I hope you learned a lot. And one last thing, don't forget in kplay.ctx to deactivate the debug mode by setting the debug property to being false. And now you can run npm run build and npm run preview to test it out, and then you can take your dist folder, zip it, and then upload it on a website like itch.io. So I hope this tutorial was useful to you. I hope you learned a lot, and if you want more tutorials like that, feel free to subscribe to my channel and check out my other content. So thanks for watching, and I'm hoping to see you in another video. Bye. Hi everyone, welcome to this new tutorial. Today we will be building a Kirby-like platformer using TypeScript and the Kaboom.js library. So Kaboom.js is a library for making games, and it can be used with TypeScript. And here I'm just showcasing the project we're going to build. So here it's a Kirby-like character that can swallow enemies and shoot stars once it is swallowed. And then here you have a beautiful level layout. By the way, I made all the assets myself. And then when you get hit like 3 times, you respawn to the original position. And that's basically it. So let's jump right into making a game like that. What you're going to need for this tutorial is, first of all, I assume a basic understanding of TypeScript. So maybe brush up on TypeScript, just watch a tutorial or something before following this tutorial. And I'm going to also use Node, so you need to be familiar with Node. So here, I'm going to open up a terminal window, and I'm going to set up the project differently than what you're used to if you have watched my previous tutorials, is that usually I would need to use index.html, etc., and then paste the links to the libraries or use JavaScript modules. Here we're going to use a bundler. It's called vite. So I'm going to do npm run, not npm, npm create at vite, vite at latest, and then dot, so that we specify that we want the project to be scaffolded inside the current folder. So by the way, I'm using VS Code for this tutorial. I recommend that you use it as well. You can install it, etc. Now, if you're familiar with TypeScript, you're probably using VS Code already, so I'm just going to go over. So after having done npm create vite at latest, we're going to select the vanilla template and then the TypeScript template. And then you should have the following files. Now we're going to delete vite.svg. We don't need that. Also, we're going to delete everything that is within the source folder, but we're going to keep the source folder. And then here, I think, yep, here it doesn't matter. Really, you can just leave it as is. It doesn't matter at all. So let's get our assets. So you will find the assets in the description. And yeah, so it's basically just one file. This file contains everything we need. By the way, during the tutorial, we will be drawing our map using an external editor called tiled, and then we will basically pass this info, this export to our JavaScript to take care of drawing. So I see that the source folder is gone, so we're gonna have to recreate it. Here we go. So now what I'm gonna do here is I'm gonna create all the files we're gonna need for this project right from the get-go, so that it's going to be easy to follow. So we're going to need a constant.ts file. This is for our constant. We're going to need a entities.ts file. This is going to be the file used to contain the logic for our players, our mobs, enemies, etc. We're going to also have a kaboom ctx.ts, which is where we're going to initialize the kaboom library and export its context and then use that elsewhere. We're going to also have a main.ts, of course, that's the entry point of our project. We're going to need a state.ts to hold a general global state of the game. So this is useful to know when to move on to the next scene, for example. And then finally, we have the utils. Utils is just going to contain one thing, I think, just related to making the map, basically. All right, so let's go to main. And before doing all of that, I forgot, we need to do npm install, which is going to install the dependencies. But we actually, I should have done npm install kaboom as well. So do this. And this is going to put kaboom accessible in your project. So once you have this, we can basically, we're gonna need the terminal to start a server in a moment, but yeah, that's basically it. Now here, let's import kaboom from kaboom. This is how you import kaboom here. And then, actually, it's not here at all. We're gonna go to the kaboom context and do this here. So import kaboom from kaboom. Once this is done, we're going to we're going to create our context. So basically it's a way to initialize kaboom. So I'm going to export k, which is going to be the kaboom context. We're going to use this constant everywhere when we need to use kaboom related functions and functionality. Okay, so to initialize kaboom, you just call the kaboom function and pass in an object which is going to have a bunch of, how do I say, options. So first, let's specify a width. Let's start with 256 pixels and a height of 144. Later on, this is the resolution of the Game Boy, but wider, so it fits within a 16:9 ratio. We're gonna set the letterbox option to being true. That means that basically our canvas is gonna scale regardless of the screen size, basically, and while keeping the aspect ratio. And we're also going to set the global property to being false. The reason we want to set the global property to being false is that we want to only be able to use kaboom related functions from this constant. That's why you need to set it to false. Now in our constants.ts file here, we're going to create one constant. Really, it's the scale of the game, because the current resolution is too small, and it's also going to act as a workaround, because in Kaboom.js there is a bug, an issue, where pixels sometimes they don't get drawn right. So you will have, let's say we have a sprite, maybe to illustrate, I'm just going to pull this out. So here our Kirby-like character, for example, you will have it drawn where you will have the image, the sprite will draw, all right, but one pixel is wider or smaller than another pixel. And to fix this, the workaround I've found is to set a scale to a value and then go to the Kaboom context and then, first of all, add the scale property. And here, first, let's import the scale constant. And then by JavaScript, you know that you can, if you have a property that has the same name, you don't have to do scale like that. So you can just do it like this. It's a shorthand. So the scale is the constant set to 4. This is what looked good. But also you need to multiply by 4 here. This is a weird workaround that I found, but it works. So yeah. And so I recommend just using it for now. If you found a way to get around this issue, then feel free to add a comment in the comment section and share it with us. Okay, so now we have our context. That's great. Now let's go back to main. And in main, we're going to have I'm going to import first our context, import k from the Kaboom context we just created. And then here we're going to have to load our sprites. Okay, so the way we're going to load our assets is going to be a bit different from other projects we've made on the channel. I'm going to create an async function. I'm going to call it game setup. Now for now, let me reduce this. Let me remove that. Okay, so we have the game setup. And in there, we're going to call all of our logic, and afterwards we call game setup here. The reason we're going to do this is because we're going to want to load the assets once, and when the player dies, we don't need to refetch the map data. We don't need to refetch the assets or something like that. So to avoid, actually, this is really to avoid having to refetch the map data coming from tiled, which is going to be the editor we're going to use to draw our maps, and it exports to a .json file, and we don't want to, every time the player dies, to redo the fetch logic to get the level layout and then redisplay it, etc. So by just having everything done within a async function, where we can use the await keyword to wait for the map layout to be extracted before moving on, this is going to be really helpful in not having to repeat this logic. So for importing the sprites, really, I'm just going to copy and paste, because this is logic that you just have to I'm going to explain it, of course, but it's a bit tedious and no new concepts or anything like that is really present. So I'm just going to explain what everything is first. So here, by using the K, which contains all Kaboom functions and methods we can use the load sprite method. This is how you load sprites in Kaboom. And by the way, because you're using a bundler like Vite or any other bundler, you're going to have this some info on how to use the functions you're using and examples, so that's pretty handy. So the first key, the first param, is the name of the sprite, how you want it to be referenced in your project. The second one is, of course, the path to the project, and here the path is just ./Kirby-like PNG, even though we're putting our assets in the public folder. And the reason for this is simply because the Vite is going to make sure that if you put this the path here, is going to append or make sure that it references the public, what's outside as well. So this is something specific to Vite. I don't know if other bundlers do this, so you don't have to do ./public/Kirby-like PNG. And then we have a slice 9 and slice 10. And the way to explain this is how to slice your image, because our image, our sprite, has much more than a single sprite within it. So it's a tile set, basically. And here you can see that we have every sprite is drawn as a 16 by 16, has a resolution of 16 by 16. That means that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different sprites on the x-axis, and that's why if I go to main.ts, slice x is going to be 9 because we have 9 sprites, 9, in the image. And then here for the vertical axis, we have 10. So you can just count them manually, but I think it's obvious. And now here is where we define the various animations. Basically, you're telling Kaboom which key corresponds to which thing you want to display in this image. So for example, for curb idle, so the main character is called Curb. So it's a Kirby-like. It's not that original of a name, but it's just for a tutorial in the end. So curb in the idle is a name I've decided to name this animation, which only contains one frame. And the first frame, remember that it starts from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. So at frame 0, you have this idle sprite. So this is the idle sprite we're going to use, and we're going to use this name to refer to it. For Kirby inhaling, so as you know, Kirby can inhale enemies. Well, it's the same thing. It's just a single sprite, and it's the sprite at index 1, 0, 1. And then curb full is when, so I guess you get the point. And then here, when you want to have an animation that has more than just a single frame, you use an object like this, where you specify a couple of keys. The first one is the from key, and you're basically telling Kaboom at which frame to start the animation. Here from frame 3, it's going to be this inhale effect. So this thing, and just to put it in action, just to show it to you. All right, so just to show you the curb inhale animation, it's this thing. When you're inhaling, you have a couple of pixels that just seems to give the effect that there is some inhaling going on. Here we go. So now if I go back to main.ts, so from frame 3 to 8, and then at a speed of 15 frames per second, this is what looked good, and I want this animation to loop. So you can decide if you want the animation to just play once or to loop forever, and we want it to loop until we just decide to stop it. So that's why I used the loop property as being true. Shooting star, it's the star here that the player shoots once they're full. And basically it's the same thing, the same logic for the various other entities. So copy the code if you haven't already, or you can pause here. So this software is called Tiled, and it's used to draw maps. And here is a map I've drawn for the first level. And I have another one for the second level. So the way I'm going to go about it is I'm going to teach you how to use Tiled for the first level. And then for the second level, we're just going to use what I've already had. And this time around, it's going to be different. We're going to export, the way we're going to use Tiled is going to be slightly different from the previous tutorials. So let's jump right into it. So first of all, install Tiled if not already. A link should be in the description. Now, there's one thing you need to do, because if you're using a big monitor, then everything should probably look very small. So to fix this, you go to Edit, Preferences, and then do Themes, and then you check mark the Use Custom Interface Font, and then you can here select the font size you want. And this way it's going to make everything much more visible. Now, I'm going to keep this as a reference as I draw the level, because otherwise it's going to be complicated. So I'm going to create a new map by going to File, New Map. And then you decide how many tiles you want and the width and height of each tiles. So here, let's start with, I think 30 by 30. You know what? I'm just going to look at the current map and see how many tiles we have. It's a 27 by 20 tile. So let's keep this. So here, new map, 27 by 20, so we can have exactly the same layout. And of course, every tile is going to be a 16 by 16 pixels. And here, don't touch anything. It's not necessary. All right, we have our tiles here. or actually we have our map, not the tiles we need to draw in. So first of all, we need to import a new tile set, and the way we're gonna do this is you specify the source. So basically browse to where you put the Kirby-like PNG in the public folder. Okay, so I have done this, so this is the path for me. Yours should be the same starting from here. And now 16 by 16 pixels, everything is all right, and then click OK. Now, once you have this, you can use the control and mouse wheel to zoom in and zoom out. So the only thing left is to start creating our various layers and placing things. So let's, of course, save. So the way you save, you do save as. I named it level.json, and I saved it as a level-1.json in the public folder of our project. So I just go here and I click. So yeah, this was a mistake for me. I just put it twice, so I'm just gonna delete this. But you should have it here. So once you have it here, we're ready to start working. All right, so now it's time for drawing. So if I look at my reference, we have the background as the lowest layer. So background. And what this is going to contain, so just make things easy for me, I'm gonna make everything non-visible. And here you can see the layout. So basically 1, 2, and then, okay, so 3 by 2. Okay. So I go here. I'm gonna select this 3 by 2. So this should be here. Yeah. And then 1, 2, 3. 1, 2, and 3. I'm just gonna zoom in with the control and the mouse wheel so you can see what I'm drawing. So basically you select tiles like this, and if you do control and select, you can also, and click, you can select more than once, more than one tile. So you can have something like that. And then here for this, I'm just gonna copy, so 2 to the side. Here we go. And then just draw it till the end, doesn't matter really all that much. By the way, always save while doing this. And then another hill, so I'm just gonna copy those two. By the way, you don't need to do control. You can just click and drag, and you can select more than one. And here you're gonna have it big map. So you know what? I'm not gonna worry about having it exactly anyway. So this is just to show you. Afterwards, I'm probably use the same map that you have here, but for the level 2, as I said, I'm just gonna use what I already had. So here, okay, so this looks like this. Doesn't have to be exactly the same. Otherwise, we're just wasting time. Then you have like that. Then maybe this like that. And a final one here. Alright, so this is our background layer. We're also going to need to add to the background layer some tiles like this. You're going to see what they serve, what's their purpose. But this is really something optional. So I'm just going to create a new layer. So by the way, in tiled, there are multiple types of layer. You have the image layer if you want to put an image as a full thing. But you have the tile layer for tiles. The object layers, object type layers are for boundaries and spawn points, so where to put your characters, a way for you to know this. And let's create another tile layer, and this second one is going to be the clouds. So clouds, here we go. And then once we have the clouds, I'm just going to select the full cloud sprites and just start putting them here. As you can see, they can overlay on top. So just put a random amount, it doesn't matter. Save, of course, as you do this. Now, the next layer is going to be the platforms. So it's a tile layer as well. Platforms. Or platform? Did I call it platforms? All right. So for the platforms, let's not stray a lot from the layout. So that's the level. Okay, so I'm going to use this, these two, oops, these two. Wait a minute, no, that doesn't work. So, oops. Where should I put this? Okay, here. And then I'm gonna expand this like that. I'm going to put this like that. Here we go. So really not much to explain here. Just draw whatever layout you want. Then we're gonna need certain structures though, just so we can have the same thing. But this is not something I plan. I draw it on paper, but I don't think it's worth, copying exactly what I'm doing. Just use the proper tiles, explore around, etc. And then here I'm just gonna have a platform. Here we go. And I'm gonna expand that further. And then like this. I think that's it. And we need another structure that is similar. So let's have this here. Expand it downward. And then a couple tiles here. How many tiles is there? 5 tiles. 1, 2, 3, 4, and then 5. And I think that's basically it. We're almost done. Oops. Doesn't matter because you can just draw over it and it will replace the tile. Okay, so we have this. Let's put a signpost here to signify the beginning of a level. Let's put the exit door. Whoops. Here. And I think a couple of grass. Here, we need to extend the background, so here in the background, gonna need this. And this. Make sure to change the layer, of course. All right, so I think we have our level, and then of course, still in the background layer, we can add this down. For the rest of the color, the full background, gonna add this using Kaboom instead. It's gonna be more performant. Actually, it doesn't really matter in the end, but I think it's better to do it this way. Because the way I'm gonna use tile today is going to be very different, and basically, you're just gonna take the image and just use the JSON to draw the boundaries on top. So instead of drawing each tiles in Kaboom, we're just gonna take a PNG. So here you can convert as a PNG. And it's gonna be very simple. Okay, so now we have this. It's time to place our various colliders. So I'm gonna create a new layer on top, an object layer this time around. I'm gonna call it colliders. And now here, the way you draw colliders by using this square, this rectangle on top here. And then here's an example. You drag, that's a mistake. You drag, come on. So basically just draw like that. So you drag and drop various squares, rectangles, sorry. And this is going to define what is collidable and what isn't. And then here we go. So once you have done this, we're done with the collider layer. And now it's time for the spawn points. So for these spawn points, it's also going to be an object layer. And I think I call it spawn points. Okay, so I'm just going to rename. By the way, you can rename by just double clicking on the layer name. So spawn points. And now what's going to happen here is I'm going to use a pin instead. So you see the pin icon, use that. And let's put our Kirby-like character here. So let's put it here where the signpost is. And here you select a name, and I'm going to call it player. This is how we're going to differentiate between all the different mobs, etc. So player spawns here. flame type mob are gonna spawn here. So flame. Oh, whoops! I created 2 pins. Be careful not to create pins by accident, because you can. So to select one, you use this button here, then you click, and then if you have the pin selected and then you try to select another one, it's just gonna add another one. We don't want that. So a flame character is gonna be here and here. Flame. Here we go. And then I think that's it. And we have our birds. So let's put 2. I wonder. Yeah, it doesn't matter the position, you know. So I'm gonna select here, called bird, and then bird, and I think we missed the guy enemy. So the guy enemy is this one. I'm gonna let's put him here. I'm gonna call it guy. All right, you have everything done. So save, and now we're ready. Oops, I created a unnecessary spawn point. So we have our spawn points, which terms where the player spawned, where the flame spawned, where the guy spawned, where the birds spawn. I think the birds are spawning a bit too far. So let's bring them down a bit so they can have a chance to hit the player at all. So here it is, maybe like that. All right. So we have everything ready. So for the exporting process, you can just use the JSON as is. But for the image, we need to hide the spawn points, hide the colliders, and then go to File, and then Export as Image. And then it's going to tell you the path and only include visible layers. And everything else should be unchecked. So now export. Now you could have decided on the background color and included it, but let's not worry about this. So export that. And then now if we go back to our editor, you should have the level displayed like this. So you can have the level as a single image. And this is more performant for Kaboom, to only have a single image to display that is relatively small and then scaled up, than having to draw each tiles using game objects. There are ways around it. So you could use a UV quad texture, but this is more advanced. So I recommend using this method. It seems very simple and can have much more bigger maps than you could previously with Kaboom.js. All right. Now that we have this, let's go back to main and import the sprites. So k.load sprite. We need the level. We're gonna call it level 1, and it's going to refer to the level 1.png sprite image that we had. Okay, let's create our scenes. We're gonna have the way you create scenes in Kaboom.js is by using the scene function. You decide on a name and you pass this as the first param, level 1. And you can have here, we're gonna use an async function. I'm gonna explain later on why. And then actually, do we need an async function here? I don't think we need it. We actually don't. Let's just have a normal error function that is going to contain the logic that is going to be executed when we go to this scene. So by default, you have to specify a default scene, and you can do this by simply calling k.go and the name of the scene, level 1, to go to that scene. Okay, once we have done that, we can write our logic from within. So first of all, let's set the gravity to being of 2100. This is what looked good. It felt good to play. And then here we're going to create a background for a game. Now here I think we could just put that logic outside. Actually, we're going to have to repeat it, because each time for each scene the background changes. Because there is actually a set background function in Kaboom.js to just set the background for everything. The issue with it is that instead of having white bars here, it's going to just use the same color of the background, and we don't want that. We really don't. So that's why, yeah. Otherwise, we will confuse the player on where is the actual limit of the level, for example. So here let's create our first game object in this tutorial. So a game object in Kaboom.js is everything that can be a sprite, a player, etc. So you in Kaboom.js you create game objects that use certain components. Those components come from Kaboom.js. You can define your own components as well. And depending on which components you add into this array, your game object will have different properties and methods that are usable on it. So I think this design is really interesting, and I haven't seen it elsewhere. I think that's what is called an entity component system, but I haven't had experience with any other one. So if you know if this is actually the entity component system, and if other libraries in other languages use it, feel free to say it in the comments. I'm curious. I want to explore it more. So we're going to use the rect component. Allows us to draw a rectangle by passing the width and the height. We can get the width and the height by calling the width and the height method of the canvas. So that's it. We want the rectangle to actually fill the full canvas so that it acts basically as a background. Then for the color, we're going to use the color component, and in there we're going to call the color class, I guess, and use the from hex method. So it's probably an abstract class, and pass in the value for the background color. And here I just gone into a sprite where I've drawn the sprite and just took the color palette. So the color for the background is this. And wait a minute. I need to add another component. I'm gonna add the fixed component. This is useful later on. It's going to make sure that this game object is not affected by the camera, and we don't want it to be affected by the camera. Otherwise, if the camera moves, then the rectangle will no longer fill the whole screen because it's going to be positioned to the left as the player goes to the right, and the camera follows the player to the right. All right, we have everything we needed. So just to run the project, you do npm run dev, and then click on the link. And then you have just an empty background. All right, so now let's write the logic for making the maps. So for loading the maps and displaying them. So what I'm going to do is I'm going to write this code in the utils.js file, ts file, sorry. And let's go over it. So first of all, I'm going to need actually don't need the context here. What we're going to need is to import the scale constant. We're going to need to have this everywhere, basically. As I explained, is to prevent pixeling the pixels, to have two pixels that aren't drawn, that don't take the same space. It's very weird, a very weird effect. But it seems to be happening in Kaboom.js if you don't, for some reason, sometimes. So that's the only fix I've found for it. So I'm going to export a function, an async function. It's kind of required because we're going to use fetch. And we're going to call this make map. It's going to take as the first param the Kaboom context. So the typing is provided by Kaboom. So all these things are going to also come from Kaboom, and that's great. And the name of the map is going to be a string. It's also going to be the path. So it's going to be used to find the path of the level. So the first thing we need is to have a constant that will hold the, maybe I should increase the font size, by the way. Here we go. Okay, so we're gonna need the to hold the map data within the map data constant here, and we're gonna use await, and then fetch, which is gonna fetch the JSON. So here we're gonna use a template string. So $name, which is the name of the map.json, and then at the outside.json to have it as a JSON. So you could have written this line in multiple lines. I assume that you know what fetch is and how to use it with the async await, so I'm not gonna spend some time here. If you aren't familiar, look at my previous tutorials or just search online. I think it's going to make a better explanation. So here we're going to use the Kaboom function to make a game object. So in Kaboom.js, you can add a game object to the scene, which basically implies that you have to create it, or you can make it, and then you can pass what you have made into the add function later on, and this is going to add it to the scene and basically draw it. So here, because we're making this a utility function, we're going to first make the map. Once the map is made, we're going to pass it to the main, which is going to call the add function on it. So make really works the same way as add. It's just that it creates the game object but does not display it. So here we're going to use the sprite component, and this is where you can define what sprite you want. And here, because remember in main.ts, we defined this sprite as being level-1, which is going to correspond to level.png. And here we have the JSON file for it, level-1.json, which we get from here. It's going to give us the map data. So if I look at the JSON export, you can see that you have layers, and each layer has a data property if it's a tile layer, or an objects property if it's a object layer, which gives us X and Y coordinates you can use. All right, so here kmake, ksprite, etc. and kscale. It's the scale component where we're going to use the scale, so to scale the map, so the sprite accordingly. We're going to also use the positional component. So this is when you want to set the position of a character. You can use, or a game object, you use the position component. It takes in 2 values, but you can pass in only one if it's the same value for both X and Y. And here for now we just use the positional value and put it at 0, 0, so that the map is drawn from 0, 0. So the X coordinate 0, Y coordinate 0. Okay. And now we're going to have to get the spawn points. So here the spawn points are going to be X and Y coordinates that are going to define what we need, where to place the various enemies, players, and etc. And for now, it's going to be an empty object because we're going to get this data from the map data, but just get what we need and store it here. So the typing for this is going to be an object, of course, but first we need to define what the type of the key is going to be. So the key is going to be a string, and the value associated with it is going to be another object, which is of the type number, and Y also of the type number. This is going to make sense in a moment. All right. So now let's iterate through the map itself, the map data. So for that, I'm going to create a for loop const layer of map data dot layers. And if you've seen earlier on in the level 1 export, you can see that we have this layers property that contains an array that contains all of our layers. Okay, now that we have this done, we're going to simply have an if statement that checks the name of the layer. So if the name of the layer is colliders, we're going to simply have another for loop, const collider of layer.objects. So here, basically, as I told you, if the type of the layer is a tile layer, it's going to have the data property, which is an array that tells us which tile to draw, etc. We don't need this for this project because we have already everything drawn as a single PNG. We just need to display that sprite. But for colliders, for object type, you have this objects property instead of the data property, which is an array containing the list of objects that is in this layer, which contains also the X and Y coordinates for each of those objects. Okay. So now here for collider of, so by using layer.name, each layer has a name, and this is how we can differentiate them really easily. So for objects, which is going to be an array, so for each element of that array, so here I'm just going to call it collider, we're going to add to the map. So map was created as a game object by using the make. It isn't displayed yet. But one thing in Kaboom.js, you can have children game objects. And this is going to be handy here because we want to add to the map the various colliders. So the colliders are going to be game objects as well. Here you cannot use the make function. You cannot do, I don't think you can do this. So you need to use the add function to add it as a child to the map. And then once map is going to be called with the add function from Kaboom, then it's going to also draw the children of that game object. So to create a hitbox, we're going to use the area component that defines a hitbox for you automatically, but you can specify a specific shape. So here the shape, I'm going to use new k-rect constructor, and it takes in as the first param the position relative to the game object. It's a vector too. And here, it's just going to be 0, 0. So a single value is enough. Now, then you need to specify the collider, the width and the height of that rectangle. And this is provided in the tiled export. If you look at the export here, you can see that for this object, we have the width and the height properties. That's very handy because we can now really know where to put those boundaries. Okay, so we also want to add another property inside of the area component. There's this thing called collision ignore, and we want basically you pass in a tag, and is going to know if collision should be ignored with a specific type of game objects. So game objects can contain tags. We haven't covered this yet, but let's add them. Those are arbitrary names that I have defined, that there's this platform tag and the exit tag, which is for the exit door. It doesn't really, for now, it's not created anywhere, but it's going to allow us to differentiate our behavior. So just to explain, here we're going to have a ternary statement, which is a basically condensed if statement. If the collider name is not the, actually I forgot to do this in tiled. So let's go back to tiled. So here in our collider, I forgot the collider for the exit. So here, I'm gonna draw, whoops, not here. So here, select the collider. You can make everything visible, doesn't matter. And then draw this. Add at its name the exit, which is going to allow us to know that this boundary corresponds to the exit of the level. Save, and then if you go back to tiled, if the collider name, so now if I go here, I can see that there is one of them that is going to contain the exit name. So if the collider name is the exit, is not the exit, basically, is not the exit, we're going to add the component called body. And in Kaboom.js, this component allows us to have collisions affected by, collisions. And if you specify within it that it is a static body, is static, and you set it to true, then the current game object here, the child game object, is going to remain static, and so that means that once the player collides with them, it's not going to move. So it's really useful for platforms. And then here I put it null. The reason I'm doing null here, it's a question mark. So the way it works is that if this condition is true, then we go here. If it's not true, it's null. So that means we add nothing, no components to our list. It's going to add null, basically, which does nothing. Here, regardless of the situation, we define the position, and it's just going to be collider X, collider Y. Nothing fancy. And that's basically it, right? And finally, a last thing. This is where we add the tags, actually. So if the collider name is not equal to exit, then this current game object that is this collider that is being added to the map is going to have the tag platform, So the way you create tags in Kaboom is just a string that you attach, that you add to your array of components. And the way it's useful is it's useful because later on you can have event handlers, and you just listen on a tag to know if this game object has collided, or a class of a group of game objects have collided with another. Otherwise, so if the collider name is not equal to exit, and don't forget the comma here, we give the game object the platform property, not property, tag. So, okay, just to recap. If the collider name is not the exit, that means that we can give the tag, the platform tag, to the current game object, current collider we created as a game object. Otherwise, we can give the exit tag. And this is going to be, later on really handy. Okay, now that we have this, I think we have everything we need. And so we can continue here. So if after doing all of that, so it was the collider. Actually, continue can be outside of the for loop, otherwise it's useless. So here, continue. So if the for loop, okay, so if the first if statement is true, there's no point in going further. We just move to the next iteration, the next layer. And now here, if the layer.name is the spawn points, this is where we're gonna have a for loop const spawn point of layer.objects for that specific layer. And then we're simply going to have another if statement. If the spawn points object we created here has a spawn point dot name. Okay, so basically the way we're doing this is that if the property, the spawn point name, is already defined, so the spawn point name is going to be the name here. So player, we're going to have an object that is going to have all the keys. So this spawn points, you can use the key, for example, player, and it's going to give you the position of the player. You can use the key guy, it's going to be the position of the guy mob. And we're making this. And here, this first if statement checks if it already exists. In case it already exists, we're going to simply add to the spawn points. So spawn points, so that assumes that there is an array. We're gonna write the condition below of if the spawn points for the specific key does it. So if the key doesn't exist in the specific in the spawn points object, then we're gonna just create an empty. We're gonna create an array, and then in that array we're gonna put the position, because we can have more than a single flame guy, a single guy mob, or a single bird. This allows us to be flexible. So if spawn point dot things going to make sense hopefully in a moment. I'm gonna push to that array that we assume that there is an array with x spawn point dot x. Y is going to be spawn point dot y, and then we're gonna continue to the next iteration because there's no point in going further. Now, if the key did not exist, that means it's the first time we're gonna have to create it. So we're gonna do this spawn point, sorry, and then spawn point dot name equal an array. X is going to be spawn point dot x. Y is going to be spawn point dot y. And here it makes all the difference. It's because we created a what's the issue? We need to what did I miss? Did I miss something? Okay, so we have spawn point dot name, and then we push, and then push does not exist on the type. I messed up. I messed up in the typing here. It's an array. Okay, so it's an array of objects like this. You need to add this bracket. So now the typing should work. Okay, we have everything we need. So just to recap again, sorry if it's getting repetitive. If the key exists already in the spawn points object, then we just add to the currently existing array that we assume exists. If it wasn't the case, then we create that array and pass in the first member of that spawn point name. So yeah. Okay, we have everything we need. And then finally, at the end, so right below here, we're going to return two things. We're going to return the map and the spawn points object. Those two things are very important. And that's it. So we can go back to main.ts. And right before we enter the scene, so after having loaded the sprite, we're gonna call, we're gonna call map. So the map here is going to be called level layout, and the spawn points is going to be the level 1 spawn points, and it's going to be getting this from await. That's why async was needed. And then make map. It's going to import this automatically. We need to pass in the context and the name, which is level-1. Now, one thing I want to cover is this. You might not be familiar with this notation. What it does is it renames the map and spawn points properties to being level 1 layout and level 1 spawn points. This is going to be handy because when we're going to have two levels, we're going to have level 2 layout, level 2 spawn points. And because the make map function always returns a map and spawn point properties, if we were to keep the same names, it would make things difficult for us. So that's a JavaScript syntax. I don't think it's very common. I haven't seen this much beforehand. So in case you were like me and you didn't know what this meant, now you know. All right, so let's draw our map. So right below in the scene, you can do k.add and just pass in the level 1 layout, as I explained, and this should draw the map, the image. So let's look at the result. Voila, you can see it drawn, but you can't see it fully for now, but it works. All right, so before moving on, let's actually write everything we need for the player, the mobs, etc. And then we're going to come back here to main.ts and add them with the spawn points, etc. So to do something like that, go to entities.ts and let's write the logic. So let's first write a function that is going to be responsible for creating our game object for the player. To do something like that, same pattern. First we pass in the context. It's going to be a kaboom context. So kaboom context. So the typing comes from kaboom as well. That's pretty handy. Then what we're going to need is to specify a position x, which is going to be a number, a position y, which is also going to be a number. Once we have all of this, my linter, yeah. So now we're gonna create a constant within, call it player, and call the k-make function that I explained earlier on. And here we're going to have a couple of components. Just to make things fast, I'm going to copy and paste everything we need here, and then go over line by line. So of course we need the scale. So import this from this constants, like that. Okay, so what do we have here? We have the sprite component that uses the asset sprites. If we go here, we named all of these assets, and then here optionally, the sprite component can take a second param, which is an object, and you can, in that object, specify the anim property and specify which animation you want to play by default. And we want to play the curb idle, which is, the name of the character, and it's frame 0. Then we create an area component. We use the area component to create a hitbox with the following shape. It's a rectangle with a width of 8 and a height of 10. And here it's going to be positioned at x value 4 and y value 5.9 relative to the sprite. This is so the character doesn't look like it's sinking in the platform. You need to put the hitbox in such a way that it's going to make the character look alright, as if it's on the platform normally. This is a bit hard to explain without visuals. So let's first write this out, and then while you're going to open the debug mode, you're going to see everything. Everything is going to make sense. K.body here component, so that the player can be collide with other game objects and be affected by gravity. The position is going to be the position x passed here, but we need to multiply by the scale. And the position y as well, we need to also multiply it by the scale so that it is placed at the right position. A scale component that calls the scale constant. This is to scale the sprite so scale the sprite so that the character takes the correct amount of space. The double jump component is something from Kaboom that you can specify a double jump and how much jumps you want to allow. So 10 jumps, so that it looks like the floating from Kirby, but it's not unlimited. And this is very easy. You just use that component. It's for free, so we don't have to write extra code to implement the feature of floating. So that's really great. The health component allows us to specify some health value, and then you can use the HP function method and the hurt function to know, and the heal function as well, to heal the life points, etc. So this is something that is handy in Kaboom.js. And the opacity is going to be set to 1. We use the opacity component. Setting it to 1 means that it's fully visible. This is going to be useful when the player is going to get hit. We're going to temporarily reduce the opacity to 0 so that it looks like it's flashing. And here, this is a new concept. Whoops. Is that in Kaboom.js you can pass objects as well as your components. So objects are going to contain properties that are going to be accessible immediately from within the game object. So if you do player dot, you can access the speed, direction, is inhaling, and is full. Those are arbitrary properties that I needed for the game. So the speed is to really control the speed, the direction for where the sprite is looking. It's going to be used for that. Is inhaling is going to be a boolean, and is full as well, that are going to be used to know when to allow for certain for the enemy to be swallowed or not, or inhaled, etc. And finally, the player tag is going to be useful. I think I'm using it later on to do the on collision logic, to know if it collides with an enemy, what to do. What we need to do though, right after, I'm going to use player.onCollide method that is available if you use the body component in the area component. And then as the first param, you specify the tag of the other game object you want to test collisions with or listen to collisions with, and it's going to be the enemy. We haven't created any enemies yet. That's normal. And when we're going to do it, we're going to add the enemy, basically, the enemy tag to those game objects. Now here, the async function, we're going to need an async function for multiple reasons. Mainly, I think, well, actually, do we actually need a sync function here? Yeah, we're going to need it because we're going to need to make the player flash and back and forth, and we're going to use a tween for that, and it gives us much more cleaner code if we use the tween. The await syntax. And here what's handy with the onCollide is that you can have the enemy game object passed in to your function here. So the second function is what runs when there is an actual collisions with the enemy. So if you have here async enemy, and then here we're going to type it as a game object, and here you need to import a quick fix, import this type from Kaboom. And yeah, so we are ready to write the content of it. So here again, I'm just gonna go faster. So here's the first if statement. If the player is inhaling, and the enemy is inhalable, you're going to see this is going to be a property we're going to create later on when we're going to create the enemies. Then what we do is we set the inhaling to being false. We destroy the enemy. That means that the player inhaled the enemy so much that it collided with the player, and that means it's swallowed. So we can destroy the enemy by calling the destroy kaboom function, where you pass in a game object to be destroyed. And then player is full is going to be true, and this is going to allow us to play another animation, and the one where the Kirby-like character is seen as full, and also is going to allow us to know if the player can now shoot a star. The second if statement we're going to need comes right after, and it's going to be this thing. Now here, global game state, we haven't created this for now, so let's replace this with level. Go to level 2 for now. Yeah, we haven't even created the level 2 as well. I'm gonna use the original, what I've already had in the original code base to go faster, because I think you get the point. So if the player HP, so HP is a method that is available since we have used the health component when creating the player object. And if it's 0, that means the player is dead. So in the case it was inhaling, or the enemy was inhalable, we would return early here, so the enemy would be destroyed. But this is when the player hits the enemy by accident, or the enemy jumps on the player or something like that. Then if the HP is 0, then we destroy the player, and then we go back to, actually we should go back to level 1 because we respawn. So we go back to the current level, and then we return early. And then regardless, so if this continues, that means that the player HP isn't equal to 0. That means we need to give damage to the player. So by using the hurt function, it's going to reduce 1 HP by default. And then you can specify a number if you want to reduce more or less. And then here is the logic that we're going to use for making the player flash blink. We're going to use a tween. So a tween allows you to change gradually a value from one value to another. And here we're going to use await because we want the tween to be completed before we move on to the next tween. So here, what this tween is going to do is it's going to take the opacity of the player, the initial opacity, and the target value is going to be 0. And the time we want to give to the tween to basically transition the player opacity from 1 to 0. So because currently it's 1, it's going to be done in 0.5 seconds. And this is the function that does the job basically of so every, I think, frame, it gives you a new value, and this value is set as the opacity. So for example, it's going to go from 1, 0.9, 0.7, 0.8, no, 0.7, 0.5, etc. until 0. And this is where you assign this value to the new value of opacity. You can do this, dot opacity. And then finally, the last param is what is the rate of change. So it's going to follow a linear function. So it's going to be done linearly. And here, once this is done, because we have an await, because this is asynchronous by default. So if you were to not use the await, you could call this, and then the code is going to continue to execute while this is still running. So to avoid this, we first await that the tween is done. So we have our opacity that goes from 1 to 0. And then once this is done, we have our opacity going from 0 to 1. So this is going to give you the blinking effect. So that's basically it. Now we have finished the on-collide logic here for now. We're going to have to come back here later on to change here to not hard code this. But for now, it's fine. Now what comes next is another on-collide, but this time around with the exit. And this is the exit door we have created, the exit collider. And here it's going to, again, I'm going to replace this. It's going to go to the next scene. So on collide with the exit, we just use the go function from Kaboom to go to another scene, and by passing it the name. And then now it's time to do the whole inhaling mechanic. So to do this, what we need to do is create our inhaling effect. So this is the sprite animation that you saw earlier on that gives the impression that the Kirby character is swallowing something and inhaling something. And it's a game object that uses the asset sprite, but the specific curb inhale effect animation as default. It has a position, a scale, the same scale, and the opacity initially is 0, and we give it a tag. What we're going to do is that this animation is always playing, but we just tweak when it is visible or not, depending on the situation, depending on the player input. And then here, what comes after is the inhale zone. The inhale zone is a hitbox that is not visible. It just contains an area component with a given shape, which is going to be a rectangle. And what this inhale zone does, it will allow us to know when the player can actually swallow an enemy. And here again, we give it a tag. Those are going to come later on. We keep an empty position here because we're going to decide on the position depending on the direction of the player. This is what this next bit of logic does. So here we have an inhale zone on update function. So you can use the on update method on every game object, and it's even a function that can be called independently. What it does, it registers an event that runs every frame as long as the game object exists in this particular form. And what it does is that if the player direction is to the left, we need to place the inhale zone to be minus 14 to 8. And because remember that the inhale zone and the inhale zone is a child, So because the inhale zone is a child of the player, that means the position here that is specified here is relative to the player, to the parent. That's why it's going to be minus 14 plus the position of the player, which is the parent, but we don't need to worry about that. And here we can specify the position. We can replace the position by doing equal and then passing in a vector 2, which is just an x and y, a data structure for having x and y values and a signal structure. Yeah, this is offered by Kaboom, but it's pretty standard in game development. Here, the inhale effect position, we're also going to modify it, but because the reason here is that the inhale effect is not a child of the player, and the reason for this is simply because we need to be able to make it to hide it or not. And it seems that in Kaboom.js you cannot hide a child, so reduce the opacity of the child without reducing the opacity of the parent. So that's why I need to manually do a player position x minus a certain value and player position y plus a certain value to get the actual position I want the inhale effect to be in when the player is facing left and in inhale effect, we need to flip X. So the animation by default is drawn from the right side. So if you look at it here, actually it's from the left side, but we need to specify. Oh, wait a minute. So it's a bit hard to explain, but basically we need to flip the animation. So if it's on the left side, we need to flip it to being true, and on the other end, which is basically the logic that comes after here, we just do false. So that it goes to the other direction, or the default direction, which is from the right. The swallowing is from the right or the left. I don't remember actually. And then finally, those are the last portion of code we need for the player. Here again, I'm gonna avoid this for now. Let's put respawn at level 1. So here another update, but this time for the player specifically. If the player position.y is superior to 2000, that means in the canvas, the more you go down, the higher the value of y. So here, what it essentially is doing is that if the player falls and exceeds this value, then we respawn the player. So basically, it is considered dead. We respawn the player by just going back to the scene, which resets everything, the state of everything. So we don't have to worry about resetting value, health, etc. So it does this automatically. And then finally, we return the player in the function make player. So this is how we get a player. And I think we're ready to just test it out to see if what happens. So in the main, right below here, right below the add, let's create our curb character. Here's the code for it. So here we call this, I'm gonna import, don't forget to import it. And then you pass in the K, and then level 1 spawn points, player, use the player key, and then there's only one player, so it's going to be at index 0, because if you remember, the spawn points are for each key, it's an array, even if there is only one, because there is the case where there is more than one. So instead of having to check when it's an array or not, we just assume that it's an array all the way. And if you know that there's only one player, you just do a 0. Past the index 0, and it's going to give you just the single player position X and Y. Now for the, actually we should have set the controls, but let's do that later. Now here, let's add the curb character to the scene, because remember in make player we just use the make kaboom function, not the add. And let's write some logic for the camera. So the camera is really automatic in Kaboom.js. There's only a few things you can do. So you don't have to write a lot of logic in that sense. So here you can specify the scaling of the camera. So we want to have it at 0.7. This is what looked good for both X and Y coordinates. So here it's either you repeat, actually in the end it's the same. So you could have decided to write 0.7 by 0.7, which is actually shorter to write. And then for the onUpdate function, this is an onUpdate that is general. So if you see here, register an event that runs every frame, not until the object is destroyed, because it's not attached to any object. And here we're just gonna make the camera follow the player in a certain way. So if the position of the curb character, the player, curb.pos.x, this is how you access the position, is inferior to the level 1 layout.pos.x, so the basically where the level starts, plus 432 pixels. This is what looked good. As long as it's inferior to that, we want the camera, so by using the campos method function, to be set at the camera the curb pos.x plus 500, and then at the height of 800, so the y coordinate of 800. This is going to allow the camera to follow the player along a certain point and not exceed that point. Because if it exceeds that point, then you're gonna see the end of the level, or basically a way for you to avoid having to show more than what you want to show in the level. So if you're at the end of the level, you don't want the player to look very far to the right, for example. And here we add the position of the player plus 500, so that the camera is really, the player is going to find themselves to the left side of the screen, and there's going to be more space available on the right side so that the player can see farther along. This is something that it's really handy, especially if you're making a Sonic type game, because you want the player to be able to see as far as possible. For this type of platform, it's not that necessary, but I thought it looked better. So now let's look at the result. I'm curious to see if there's anything going to change. All right, we can see our level, but now we don't have the movement controls, and this is what we're gonna deal with in an instant. Okay, so now that we have the camera working and the character being displayed, I think it's best to just start working on implementing the player controls so that we can truly see if the camera is actually working. So by player controls, I mean all the mechanics of the Kirby, so moving, swallowing, floating, etc. To do something like that, I'm going to go to the entities folder, file, sorry, not folder, and in there, we're going to create a function right below. So this function is going to be called export function set controls, and it's going to take two things: the context, as always, but it will also take the player object. Now here I could have simply gone with the game object here as the typing, but we want it to be specifically for the player. So this is where we're going to create a new type. So the way you can go about creating types is either you create them all in a folder, in a specific file, and then you pull them out from there, or you create them where we need them. And really, here in this project, the current state of the project, I might expand the game later on, but on my own. But for the tutorial, really, we're not gonna export any typing really. There's only this type, and you could have decided not to use it, but I think it's it's a best practice to create a specific type for the player, because there are some behaviors like you're expecting that the game object passed here in the set controls function is going to have some components, some necessary components. So the way you type a game object in Kaboom.js, you can take the default game object type and then add to it here the various components you need. So we want the following, so I'm just going to copy and paste it and then talk over the content. So this is going to go much faster. So here is the typing definition. Now all of these need to be imported from Kaboom. So update import from Kaboom. I should have just clicked here and I'll add all missing imports. All right, so to explain. So the player game object is a type that is a game object that has the sprite component, the area component, the body component, the positional component, the scale component, the double jump component, the health component, and the opacity component, and it has the following properties: the speed, the direction, is inhaling, and is full booleans. And this in make player, you can see that those were the properties here. So the goal of this is that if somehow you were to use this set controls on a mob, for example, which is just a regular game object, then you would have squiggly lines and TypeScript will tell you that, hey, you're not entering the correct type. So I'm just going to put player game object here. And now let's write the body of this set controls function. So let's do that. Give me a second. Okay. So first of all, what we need is actually, I need a reference to the inhale effect that we had. So I'm going to create a constant called inhale effect ref, which is this here in the original code base that we had. And this is a way to neatly get any game object you need, is you pass in the tag to the get function from Kaboom, here inhale effect, and it will return an array containing all the game objects that have this tag. So here we're expecting one, so I'm just gonna take the one at index 0. This is going to be useful because here in the controls, in the input, is where we're gonna decide whether or not to show the inhale effect of the Kirby-like character. So really, we need to start coding the player movement. The way you do this in Kaboom is by using the onKeyDown function, and it passes to you the key that is being pressed. So here I could just have a switch case statement. So switch key here. You could have left it as an if, but it's more concise to use a switch case statement. It's a matter of preference. So also sometimes it's clearer to just use if statements. So for the left case, we're gonna first set the direction of the player like this, since we previously decided that those are the properties we needed, and because we created them, we added them here, they are available to be modified in red here, in as long as you have access to the game object for the player. So here we're gonna change it to left, or set it to left, regardless of what the previous direction was. We're gonna flip the player horizontally by using the flip X property. This is offered by Kaboom if your game object has a sprite, uses the sprite component. So we're gonna have true, set it to true here regardless. And then finally, to move the player, it's in Kaboom.js, it's really simple. You call the move function and passes in a velocity, an X velocity or a Y velocity. Here we just pass in the player's speed, and Y velocity is 0. So the player is going to move here to the right, but you have to do minus to get to the left. This is very simple. And then you, of course, you have to break. Otherwise, the other cases are going to run. This is something like in JavaScript. I don't think in other programming language it's the case. Now we have the right case. And it's basically going to be the same thing. So I'm just going to copy and paste, but just different values here. And then after that, we have the Z case, the case Z. When the player presses the Z key, this is where we're going to basically make the character inhale. So simply within this, we're going to have an if statement. If the player is full, then we need to play the curb full animation. Curb full animation. Once this is played, or is playing, we can show the inhale effect. No, actually hide the inhale effect by setting the opacity of the inhale effect ref to 0 if it were visible. And then we break here. And then in here, and then right below, we are still in the Z case. If that was not true, so the player was not full, that means it's time to let the player inhale. So is inhaling is going to be set to true. And then we're going to play by calling the play function the curb inhaling. That's the name of the animation. And we're going to show the opacity. So we're going to set the opacity to 1 so that we can show the inhale effect. So now that we have this, we can break for real as well here. And then we need to, when using a switch case statement, to have the default, which is going to be empty in this case. So now we should be able to move left and right. Let's look at it. So if I maybe I should refresh the page. Oh, I haven't called it, so it's not gonna work. So if I go to main.ts and I go right before adding it to the scene, let's call the set controls function. It should be imported automatically and pass in the curb character. Of course, the context first as well. Now, if we look at the result, I should be able to move, and then when I press Z, I'm making the sound effect with it. But for now, you see that even if I I stopped pressing the key, Z key, the animation is still going on because we need to have a handler that checks when we release a key as well. And by the way, if you press F1, you can see the various collisions here. So yep, let's go back to the code base. Let's go back to the entities code. And here I'm just going to collapse the onKeyDown function. Now on key press this, let's implement the jumping first, I think. And then we'll go with the onKey release. So here, same logic. We pass in the key. Oops, not page transition. You know what? I'm just going to copy the code just to be fast and then talk over it. Maybe I should start just doing that for all tutorials. So on key press, we have the key here. Here, this feels like unnecessary code. You could have just have a simple if statement. I'm gonna leave it though, in case you want to make allow multiple characters to be used for jumping. And here we can use the double jump method. And the reason we can use that is because we used, when defining the player game object, the double jump component. So this is what allows the Kirby-like character to float, to jump 10 times basically. Okay, now here it's time to do the onKey release. So onKey release. Here you go. And then again, here it's a switch statement. I don't remember if it's going to be that much useful. It's a single case. You know what? Just to make the code better, you know, if key equal x. Let's remove all this unnecessary stuff. Let's not over optimize, or yeah, and even this is not necessary. And then I of course need to remove that for the linting, the formatting, sorry, to work. So here, if the key, you do this. Actually, yeah. Anyway, yeah, there could be say that the switch case statement syntax is not that concise. So yeah. Okay, so on the onKey release, we have the key, and then here I'm gonna use a if statement instead of a switch case again. And here, if the Z key is pressed, we're gonna do a bunch of stuff. So here, if the Z key is pressed, and we have another if statement. Usually I don't like that, having multiple ifs within. Let's keep it as is for now, and I'm gonna see if it makes the code any more difficult to understand, or if it can be improved later on. So if the player is full, we do something. So we need to play the curb inhaling. So the reason we're playing the curb inhaling animation when the Z key is released, if the player was full, that means they swallowed an enemy, is because the animation, so the image for both swallowing, inhaling, and shooting or spitting out the enemy, the star, is going to be the same. I thought it would work for both cases, so that's why it's playing this animation here. Okay, now let's do a const here and call it shooting star. And this is going to be a game object that basically the projectile, the star. We're going to create it. It's a disposable game object. We just create it here, and we write everything we need for it here. No need for modularizing. Though if you were to expand this game and maybe make, you know what a good exercise you could do with this is try to make implement the copy abilities of Kirby. So Kirby, except for the first game, not only can he inhale enemies and throw stars and stuff like that, but can inhale enemies and then use their powers, so become a fire Kirby, etc. Okay, so for shooting stars, yeah, we just going to need to use the sprite component. And here, the animation we're going to specify is shooting star. I think we already defined it earlier on. And we can also set the flip value, so the direction from which you want the animation to play within the second param. Because this is very disposable and we won't need to change the direction afterwards, because what happens is the projectile is shot, and then it just goes to and as soon as it either hits an enemy or a wall, it will destroy itself. So here we can do a simple, depending on the player direction, if the player direction is equal to right, then this expression will evaluate to true. And if it evaluates to true, that means we need to flip X. So that means we're going to flip the star to be at the right direction, because by default it is to the left, so, like that. And that's basically it, I think. Yep. Now we can continue on. So k.area. Here, I'm going to have a shape. Now here, you can tweak these values. So I'm just going to copy over the code that we need, if it's at all possible. Let me just copy the whole thing. So I'm going to copy just the rest of the code for this game object, and I'm just going to go over it. So here we have a specific shape, which is a rectangle with this offset and then 6x6, etc. By the way, if we look at the output and I press the F1 key, you can see the the box, the hitbox for the Kirby-like character. So here, and depending on how you position the sprite, I made sure to position the sprite a bit above. That's why the offset here was a certain value. I think it was where it was 4 by 5.9. Play with those values and you're gonna see what happens, and get a better understanding than me trying to explain it to you with words. Okay, so we have the shape of the hitbox defined here. Then for the position, it depends. If the player direction is to the left, then the player position dot x is going to be minus. We're gonna take the player position to the. We're gonna take the x position of the player, and do minus 80. Otherwise, if it's to the right, plus 80. And this is so that when you shoot from the left and the right, it corresponds, because the star is mirrored and it's going to go in a different direction. So play with those values, you're going to understand. Here for the Y, there isn't much difference between either right or left direction. So basically this what looked good, taking the player position, the Y position of the player, and then adding it 5 to it. You can play with those values if you'd like. And then of course we need the scale component as I started this game, because as I said, the pixels aren't going to be drawn properly, where one pixel takes 1 pixel space, but a second pixel can take 1.5. And this distortion is a bug in Kaboom.js, and the way to fix it I found is this. It doesn't happen always, so I think it depends on your resolution. So if you were to make a game that is of a higher resolution, you wouldn't have this issue. I didn't have this issue very much before. So it really depends on the resolution you pick, it seems. And then here, depending on the direction, we can use the move component. The move component will just move the sprite, the game object, towards a direction. So that's the first param. If you hover over it, you can have a direction. It's either a number or a vector 2. And here I'm just using the constants provided by Kaboom, which is the left and right direction. So if the player direction is to the left, that means we need to make the shooting star, move to the left. Otherwise, we need to make the shooting star move to the right. And then we add the shooting star tag here so that we can later on have not later on, just right now, basically. I'm just going to copy and paste it as well. So right outside of this definition, I'm going to have this onCollide event listener actually, yeah, this tag is going to be useful, I think, later on for other things, other event listeners, because we don't need the tag because we already have a reference to the shooting star here. So if the shooting star onCollide with the platform tag, so with any game object that has the platform tag, then k.destroy is using the Kaboom function to destroy the shooting star. So that's basically it. And then here it's done. And then finally, what is needed is simply to put the player is full back to being false, since the Kirby-like character has just shooted the star, so that they should be able now to swallow someone else, another enemy. And then we're going to use the wait function from Kaboom that is going to wait 1 second before making the player play the idle, the curb idle animation. Curb idle animation. Here we go. Here, in case you didn't see it. Here it is. So this is a Kaboom.js function to do that. And then we return early. The reason we return early is that if we don't do this, we can just go here and just set the inhale effect the opacity to 0. The reason we're going to set it to 0 is because now the Kirby-like character has done inhaling, so we don't want to show the inhale effect. And then we set player is inhaling to being false as well, because they're no longer inhaling anything. And then we put the player back to idle. That was the case if the That was the case if the player was not full initially. So can we make this better by removing this if statement? I think we could have this as a second condition. And then I think it's best to just keep it as is. By the way, the source code is available in the comment not in the description. So feel free to refer to that if you want. Okay, I think our code is done for this. So let's try it out. Let's try the output. So I can jump, I can inhale, and then when I stop pressing, it stops. And then you can see the inhale zone in the hitbox. So looks nice. And then if I just go here, there's no level 2 for now. Okay, our game is working. And one thing about the camera, I said that it follows you up until a certain point and then it stops here. Oops. Okay. And then one thing I noticed is that we don't see the little thing here at the bottom. So if I go back to main.ts and maybe instead of this I put 900 here. You see this, I wanted to see that, so maybe 850 is going to be a good value. But then again, this is due to the specific map we drew together instead of the original map from the original source code I made. Okay, maybe a bit more. 70 should be fine. Does it work? Okay, it seems to look good. Okay, now it's time to work on making the enemies inhalable. But before doing any of that, we should probably write the code for the enemies. So I'm going to go back to entities. I'm going to collapse this as well. Let's write another function for making the flame enemies. And to go fast this time around, I'm going to just copy and talk over it. I think it's going to be better. So here it is. But it expects the... Anyway, yeah, let's forget this for now. Okay, so we have this function called make flame enemy. And it's going to be the flame NPC here. Enemy. So to make this, we need the context. We need a position, X and Y position. Then we use the same thing, but this time around I used the add function. That might be because we just created immediately. I don't think it's that big of a deal. Anyway, it doesn't matter. For this game, it doesn't matter if you use make or add. Just that if you use make, you have to use add later in main.ts. So here we have a flame character. Basically, we set the animation, we set the scale, we set the position, which needs to be according to the scale. So that's why we multiply by the scale. Then we have the area, which is the hitbox for it. And then the collision ignore, which is it needs to ignore collisions with other enemies. The reason for that is, and we use the enemy tag here. The reason for that is that, for example, the bird is flying on top and then the flame is going to jump and we don't want both to collide. We want both to continue doing their thing without any collisions. So that's why we ignore the collision if it does occur. So it has no effect on the game. We use the body component and then the state. This is something new because we're going to define the AI for this little flame character. And the way you do that is using a state machine, and a state machine contains basically different states. And then for each state, you need to define the behavior and what happens, what makes it go to another state, and what happens when it enters the state, and what happens when it remains within the state. So here, the state component in Kaboom.js takes a default state and the list of all possible states. Here, I've defined my state machine as being two states, idle and jump. And we start with the idle. And here, finally, we have just add the enemy tag, and this is going to be useful for both this, so that the enemy can ignore collisions with other enemies. So, for example, two flame characters, if they were to collide together, we don't want them to have any effect. So we don't want them to push each other, and it could be fun and weird to not have enemies being able to collide with each other, etc. But it creates too much unpredictability. All right. So how do we define the state? So here, once you have used the state component, you use the onStateUnter function to define for this state what happens, what is run when we enter the idle state. And here I just use the kaboom wait function, but this time using the await keyword. This is just so we have it we have it sequentially. So the wait is asynchronous by default. That means if you don't put the await keyword, it's going to run, and the rest of the JavaScript code is going to run after it as well. While by using the await keyword, what it means is that we wait 1 second before moving on here. So that's why I wanted this await here, so that I don't want to move on to another state before we have waited 1 second. So once we wait 1 second, we enter the jump state. Once we arrive in the jump state, we define here what we do in that case. So on state enter jump, we just make the flame jump, and we can use the jump function provided by Kaboom if your game object uses the body component. And here we specify a jump force. This is just so like the name, it's the force of the jump, and it can be tweaked, and I think 1000 was the value that looked best. And then finally, once this is done, there is another thing you can define for a same state. It's called onStateUpdate. And here, as it says, register an event that runs every frame when in a specific state. So while we are in the jump state, we want to run the following. So if the flame is grounded, this is a function method provided by Kaboom if you use the body component. So so it basically checks for you if the flame is on the ground, on a platform. And if it's the case, then we can just enter the state idle again. And basically this is a simple AI. So just to make things clear, what this AI does is just it waits 1 second, it jumps. Once it hits back the ground, it enters back into the idle state, waits 1 second, and then jump again, etc. So it's not something fancy, but yeah, it's an obstacle, I guess. And then we return, of course, the flame. And then we return, of course, the flame game object. Now let's make this make inhalable function that is going to be applied to all enemies. So right below set controls, I'm going to, again, copy and paste the code for it and then go and explain it. I think it's going to make much better explanation, so I don't have to focus on typing while explaining. And I don't waste time typing while I could be explaining. Okay, so here, make inhalable. This is the function, takes the Kaboom context and a enemy, which is just a game object. So here we specify a bunch of onCollide event listener. So when the enemy collides with the inhale zone by using its tag, we make the enemy is inhalable equal to true. Now here, it didn't exist before, so not only you can create properties, so you can create properties on the fly for a game object, and maybe it would have been better if here in the game object you want to create, you create the property first instead of just relying on this. But for this tutorial, I think it's fine. So if the onCollide, so if the enemy collides with the inhale zone, then we set is inhalable true. So the inhale zone is this. In the game, when I press F1, it's this part. And by the way, the debug mode tells you the position of each game object and also the tag. For example, this is a platform, this is the exit, and I think that's it. And this is the inhale zone, this is the player, etc. Okay, now that we have something like that, we have the onCollide end, which also exists. So as soon as the collision is over, maybe because the enemy moved away or the player moved away, then we set the is inhalable to false, so that the player could not inhale someone not inside of the inhale zone. Finally, we have also the enemy on collide with a shooting star. This is where the shooting star becomes useful, and we run the following function. What is really handy with on collide is that it provides you the game object that is the tagged here. So it pulls it out for you, and you can have access to it. So here I can just do destroy the enemy and then destroy the shooting star. One thing I want to make sure though is in set controls, maybe I wrote destruction logic here. Where is it? Where is it? Here. Okay, I wrote for the platform here. So if the platform collides with the shooting star, then the shooting star is destroyed. But this is a different case that we have here in make inhalable, is if the enemy collides with the shooting star, we need to destroy both the enemy and the shooting star. That is here, provided here. And then here I use the player ref to get the player. So the same way I did it earlier on with another game object, I don't remember. And then here on update register an event that runs every frame as long as the game object exists. If the player if the player is inhaling and the enemy is inhalable, that means we can actually do the inhaling. And then here, if the direction is to the right, that means we're going to make the enemy move towards minus 800, so to the left, with a velocity, x velocity of minus 800. And if it's not the case, then we assume that it is to the left side, and then we make the character, the enemy inhaled, move to the, actually it's the contrary. So if the direction of the player is to the right, we move to the left, the enemy move to the left. Otherwise, it's the reverse. And that's basically it. And then now here, when I commented out make inhalable, I can just comment this back in. And then, yep, that's it. Now let's write in main.ts the logic for that. So right below where we wrote the logic for the player, let's do it. Let's do the same for the flame enemy, and it's going to be very simple. We just need a for loop, and here I'm just gonna import here and save, of course. So now const flame of level 1 spawn points dot flame, and then it gives you all the flame characters, mobs, and then you can just display them like that, create them, and that's it. Okay, now if I look at the result, make flame enemy is not defined. Really? Maybe I did not make flame enemy is defined. Maybe the import wasn't right. What do you mean it's not defined? Did I use the proper tag? Let's look at here. We have flame. If I look at level 1, we have flame, 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 flame. Everything seems to be correct. So why it's not working? Let's look at. Okay, it's working. It's just it didn't refresh soon enough. All right. So as you can see, I can swallow and then I can shoot. I can swallow. Oops, I took damage, and then I can shoot. And that's basically the game. Everything from this point now is just improvement and increasing the scope. So here in entities, let's write the code for the guy enemy. I'm just going to copy and paste it. So, yeah, so let me just, there's still some explaining to do. It's not exactly the same thing, but it's going to be mostly similar. So here I paste it, and then let's go through it together. So we have the make guy enemy function, takes in the same params as make flame enemy. Basically the same components, just the different animations. And for the state, it's okay. Here I used is inhalable. I added it to make flame enemy, to the guy, but not here. So what we could do is just let's add it, you know, just to make things correct. So I'm gonna add is inhalable. Gonna set it to true, to false. by default. And here we go. Okay, so the state machine here is going to contain more states. It's going to take, actually this jump, I did not implement it. I wanted the character to jump after moving left to right. You can do that on your own, but it has 3 states: idle, left and right, and it start at idle. So at the idle state, same thing, we wait and then we go to the left state, we flip X false, we set it to false in case it were flipped to the right, which does occur when the right here, using right, when going to the right. And then we wait 2 seconds before going to the opposite state. And while it's doing this, while we're currently in the left state, then we move to the left at a certain speed defined here. And this is the same logic but duplicated and just tweaked so that it's the same for the right. Now we flip X to being true because, you know, the sprite here, the guy is facing left instead of right. And then here we move with a positive value instead of a negative value. Now if I go back to main.ts and I go back here, it's another for loop, same logic. Import this if not already, save, and that's it. Now the last enemy is going to be a bit different. The bird enemy, it's not going to have an AI really. It's just going to move into a direction and that's it. And it's going to spawn continuously. So I'm going to remove this, not remove it, I mean collapse it. And let's write the last function for the enemies. And then we're basically done with this. So here, I forgot to have the closing function. The closing bracket of function, sorry. Okay, so we have make bird enemy. Takes this time around 4 params instead of 3. Only difference is the speed because it's going to vary each time we create a bird. So here we have a bird enemy, basically the same thing. And then is static being true. Now this, it isn't necessary to have it to be static. So let's remove that. And it's going to move to the left by default at a certain speed that is defined by here. And then we have the off-screen component, and this is something very interesting if you're planning on making a more expanded game, is that you want things to not render when they're off screen at a certain point, of course. Here, if the distance from the viewport is higher than 400 or equal, then we destroy the bird, because we just want birds that comes from the right and goes to the left indefinitely. And for all those birds that were to the left, then at some point we want to destroy them to free space, I guess, so as to our game not to have a frame rate that collapse and overwhelm our web browser, I guess. Okay, so we make it inhalable, the bird, of course, and then we return the bird. And now what changes is here, instead of having a simple for loop, we're gonna have a for loop as well. And then here, of course, import make bird enemy, and here we're gonna use the loop function. So here for bird in level 1 spawn birds, we have here a constant that defines the possible speeds we want to have, 100, 200, 300. And then we use the loop function from Kaboom to basically loop. Every 10 seconds, this will run. So it's a cleaner syntax for set interval, if you're familiar with the JavaScript function for that. Now, make bird enemy is going to take in a random element from here. So it's going to randomly pick either 100, 200, or 300 by using this logic. So this is a common piece of code you see online, where you do the math random times the length of the array, then you floor it, and this gives you an element within the array that is random. And that's it. I think we have finished. So if I go back to the browser, you can see the guy is walking. And if I were to just shoot, now you see that they didn't appear. Okay, now I understand why I had the his body static because it's affected by gravity. So if I come here, so if you're far enough away, you're gonna see the star. Otherwise, if you're too close to an enemy and you shoot the star, it's going to disappear. The star is both the star and the enemy is going to disappear too fast, I think. And if you want a better feedback loop for the player, I think it's best to change this. So as you saw, the birds are just falling down, and that's because we removed the is static, and we don't want that after all. So uh, it makes sense to have here is static, so that it's not affected by gravity. The birds. Now if I go and I look at the birds, you can see they're coming in, and I can shoot them. And here we go. Now here it is. And then of course there's no level 2 for now. And you know what? I think I'm not gonna implement the level 2. I think try it out on your own. Try to create a second layout. Use the thing I've explained here and do the transition between. Yeah, I think it's best. And of course, you can reference the original source code. I have the GitHub repo. Feel free to download it, look into it, etc. So yeah, I think I'm gonna end the tutorial here, just not to make it too long. And of course, the concepts, I don't want to rehash the same concepts all the time, but I hope this tutorial really was clear, that you understood how to make games using TypeScript and Kaboom.js. So yeah, thanks for watching and subscribe for more content. So is it running at 60 FPS? It is. All right, thanks for watching. Bye. All right, so I forgot a very important part of the tutorial, which is how can you actually publish your game. So when you're using a tool like Vite, like we did in the Kirby tutorial, you need to create a vite.config.ts file, and then here you do import define config from Vite, and then export default this, and then here you need to specify those those two properties. So the base needs to be dot slash, otherwise when you're gonna do npm run build, you're going to get something that won't work. So if you open this using, for example, live server, what's in the dist folder, then it's going to be, how do I say it? You're going to get an error. Now you need also to disable the minification in Vite. This is an issue with Kaboom.js specifically. I don't know in the future if it's going to still be an issue. So try it without and with. So once you have done this configuration in vite.config.ts, which should be at the root level of your project, what you should do is just run npm run build. So npm run build, and then it's going to run your compiler TypeScript code, etc. So then you should see a dist folder appearing, and this is the folder you need to zip. You need to zip this, and then you can put it on itch.io, for example. So here, if I right click and open it with live server just to test out that things are working, you can see that the game is actually working. All right, that was a little bonus that I forgot to include. So hope you're still watching at this point. Thanks for watching. Bye.